objectives of the workshop. First of all, a warm welcome and good morning to all those who are attending online and offline from the Department of Medicinal Chemistry, NIPER, Guwahati. We are thankful to our Director, Dean, Registrar, CC, and the staff, and of course the funding agency, Ministry of Electronics and Information Technology, for providing us financial support. This workshop aims to introduce young medicinal chemists and drug discovery enthusiasts to modern AI-based drug discovery methods, and also to get exposure in this field. Sessions have been planned to introduce them with fundamental concepts of AI, quantum, and computational chemistry, also reactivity, binding kinetics, even green chemistry, and other areas of drug discovery. Real-life examples will be provided on how concepts are applied in the pharma industry. Eminent speakers will join us and discuss the role of machine learning in the area of protein therapeutics, QASR, biotech industry, and chemical biology. These talks will be streamed online on YouTube and will be available for future reference also. Online participants can post their questions on the YouTube chat box, and we will try to address most of the questions if time permits. With this, I welcome you once again to the workshop, and thank you very much. Over to Krishna. Thank you, Dr. Vaibhav. Now I request our Director, Dr. Inhibition to deliver the welcome address and also to introduce the chief guest to the audience. Thanks to Professor James, who is going to say opening remarks and importance and significance of this particular workshop and as a chief guest. Welcome, Professor James, sir. And before going for the actual content of this workshop, let me give you a brief outline about this institute, about NIPER Guwahati, which was established in 2008 in first National Pharma Institute in Northeastern region. Later on, it was shifted to the permanent campus in 2019, and our full-fledged operations are started in 2020. It is going to be dedicated to the nation in the month of February by secretary and other dignitaries. This institute has secured 11th rank before last year, and last year we got again it was dropped down due to the pandemic to the NIRF ranking 19. Whereas this is the first NIPER to have nearly 8 national centers, Center of Excellences funded by various institutes like DONOR, DST, DBT, and so on, Ministry of Commerce and all. And there is one more center pertaining to the medicinal chemistry and drug design, Advanced Center for AI-based drug design in medicinal chemistry, also was sponsored by mighty Ministry Government of India with a budget of almost 1.5 crores. And I am very happy to share that we have entered into MOU with CDAC recently to take the maximum advantage of Param supercomputing facility apart from the software freely available to the nation from the CDAC server. And we entered into MOU recently that is also going to be used by NIPER students through virtual.
Hey, Sahanuda asan ni?
Prior to this,
Sahanuda, 1 minute.
we are already working with the Param Ishan, which is located in Naipur, in a virtual mode. And we have our one national supercomputing mission project, which is connected to the IIT BHU, and we are growing slowly in this direction to give a flavor and importance to our students who are interested in the drug design to be taken as the potential career.
तुम मीटिंग में ज्वाइन किया या उसमें ज्वाइन किया? यूट्यूब में ज्वाइन किया ना सर? या मीटिंग टीम्स में ज्वाइन किया?
USA, AstraZeneca and Pfizer as well. The demo sessions are systematically arranged by the organizers with the help of OpenEye Scientific and BioVR Discovery Studio. Artificial intelligence and machine learning, these are all the buzzing words for the past few years people are talking. But whereas our faculty, they are literally working in this area, not only in drug design, in various areas. Recently, I am very happy to share Pharmacokinetics department, which is the backbone of the formulations of any drug, but to make it as possible viable and applicable and adaptable by the public through AI technologies. That is also taken up by our pharmaceutics division, and they have published more than 3 to 4 papers. I am also happy to share Professor Jimmy sir and one of our faculty with artificial intelligence. The 3D model is developed, and it is going to be in the market very soon through a window of AMTZ, Andhra Pradesh Medical Technology Zone, and they have given some space to incubate our idea there, so that the industry is also ready to take up this product, so that the industry academia, whatever we are talking for the past 4 decades, we are going to see the light of the day in the Naipur campus. And this conference of 72 hours will be certainly beneficial, useful and resourceful for the young generation who are interested in this line. And I am very happy that earlier also the biotechnology division students, which is not directly connected to this medicinal chemistry and drug design, they have participated in writing the Python programs, especially from the taking the data of the PDB, that is protein data bank, and they have come out with successfully the small solutions given to them by our earlier colleague, late Dr. Hemant Srivatsau, who is the founding faculty of this CCC department, that means Computer and Communication department under the medicinal chemistry. Now it is a time where Dr. Vaibhav will take it to the further heights, and Naipur will support all angles for success of this particular program. And this is my happiest duty to be taken over introduction of our eminent speaker today, who is the chief guest of this function, Professor D.V. Jamis, who is the Padma Shri Awardee in 2014. He got his PhD from Princeton in 1978 with John Hubel, and he was the postdoc fellow at Cornell University with Rhoda Hoffman, and he served in the many national institutes like IAC, Bangalore, director of ISAC Trivandrum from 2008 to 2013. He is the recipient of various awards. Scientist of Aadhaar Award in 1994, followed by J.C. Bose National Fellow. He is a pioneer in the quantum chemistry and applications of various molecular systems. He discovered electron counting rules, often called Jammy's rules, which explain the structure of gluons. I request him to deliver the opening remarks and address the students that will certainly boost the academic flavor and Naipur Kavati. Thank you very much. Jai Hind. Over to Professor G.
Sir, you are mute.
Thank you, Professor Murthy, for the kind words of direction. In fact, I'm not an expert in the area, but I met Professor Murthy, who was at IICT, studying Naipur, and his colleagues asked me to come and inaugurate. I wish I could actually come there and inaugurate, but unfortunately, But I'm so glad that that institute has taken the initiative for this particular program for drug design and medicinal chemistry using computers. Now, there are lots of experts here who will speak to you. They are the movers and shakers, so to speak, in the area in the industry, and I'm so glad that it is materializing well. The connection to IICT for this Hypergravity is not mistaken at all. Professor Murthy spent a lot of years here IICT, and Professor Shastri was there and many others. But it is natural that the application emphasis of natural products, pharmaceuticals, and definitely advancement in this through this new medium of computational methods and methodology are the need of the hour. In fact, the students of artificial intelligence and machine learning used to say that if you did not know any chemistry at all, it doesn't matter, but from the computational modeling, we would have learned the Ramachandran diagram, even though it wouldn't have come in a conceptual way. But it is important to realize that there is an evolution that has happened over the last 50 years or 60, 70 years about chemistry in general and medicinal chemistry and pharmaceutical industry at large. The reason I say all this is that we have talked about always empirical force fields that would describe molecules, whether it is biologically active molecules or small molecules, large molecules, in the 60s. And in the 70s, there was, of course, the dynamics coming in using empirical force fields. And towards the late 70s, people have ended up to have force fields coming in from semi-empirical molecular orbital calculations. And for some time, it was felt that that is sufficient. And soon enough, quantum mechanics became more accessible, and it appeared as though one could jump and go away from empirical force field or semi-empirical calculations, combination modeling. But soon one realized that that modeling is restricted to very few atoms, very few, molecules with very few atoms. And then the ingenuity came in, and we had QM/MM calculations where we described a larger system, an enzyme with its active site alone being described by quantum mechanical methods, and then the rest of it through empirical force field or semi-empirical MO method. And all along, there was this question whether one should really go into dynamics all the time. But it is clear that for life comparisons to anything, we need to have the time evolution built in. And so we have now all these popular methods for molecular dynamics using force fields that are generated on the way or changed as we move along, or even pure classical force fields. What is important is that in the midst of all this, we should be asking several questions. One is are the medicinal questions or the questions of drug design that we are asking? The drug and the context is the most important one. Right? We have the facility, but with these facilities, is it possible for us to ask the most important question that is possible? In other words, we should not solve the same problem again and again. There are a large number of pressing problems, and we should not hesitate to go into that. That's a practical problem. Obviously, being in Ligand, Computational, and other institutions, other branches of Ligand, we know that yes, there are problems that are solvable and there are problems that are pressing that it has to solve. So this is something that you ask again and again. Is this the best that I can do, or is this the best target that I should worry about? Right? Is there something more pressing than this? From a point of view of our national priorities in terms of solving health issues. The other is that when we have lots of methods, there is a decision to be made which way the life should move. Obviously, everything cannot be done by everybody. But fortunately, perhaps you will see in the first presentation, which is by Professor Lalahari Shastri, an attempt to have a platform where people from various places could not only use a set of connected programs, but also contribute to this in ways that are not thinkable earlier. So a collective endeavor of this kind is available. Now, when you have a collective endeavor of this kind that is available, it is still necessary to see and to understand how it all works. Do not use it as a black box. The reason I say is the following. Often I see researchers moving back and forth between classical force field based molecular dynamics and then to ab initio dynamics and then to electronic structure calculations of the active side. In other words, switching back and forth between different models and not realizing the limitations of these different models. So it is absolutely essential to realize that one has an array of facilities available, programs available, methods available, but one should know what one is doing and which is the best one for a given purpose. Of course, a combination of all of it might be needed, but it is still necessary to see when one shifts from one method to a totally different method, from classical mechanics to quantum mechanics, from ab initio dynamics to a set of reaction coordinate-based static calculations. Sometimes even that might be needed in the beginning. So these differences should be there. The other is that one should also be keeping in mind that at the end of a long research project to see what is the best drug that one can get by trying large number of small molecules that is there in the library, one gets a result. For the moment, that result is sufficient. Because that was the target. We would like to see what is the best drug available for a particular problem. And once we got that drug, it is good to go back and see why the program gave that particular molecule as the best drug. What is it that has made this particular molecule that we have got as the best one? Can we understand why the numbers have come the way it has? Is there anything more that one can learn from it? Of course, the pharma industry can immediately take the drug and keep going. But beyond that, is it possible to see some factors that might be transferable from one problem to the other, so that when we are coming to the next problem in medicinal chemistry and we are looking for another drug, what is the context in which the earlier study was successful? What parameters of this particular small molecule compared to the 50 others that had been shortlisted by, let's say, the machine learning algorithm? How does this one comes the best, happen to be the best? And often such answers are not easily available, but it is worthwhile to search and gain that knowledge. Once we have that knowledge, then while the program might still help us to select from 1,000 small molecules available,
or 10,000 small molecules available to come to 50. Perhaps you might hit at a small number of 10 molecules even before the program can get there, right? This would help. The other is that the process might, this search for an answer might help us to see a totally new molecule, right? More than what the program has provided, more than what the small molecules library has got, with you. You can think of some very innocuous change that might do the trick. These are not always successful, but the attempt should be made at every stage. Why did we get this particular result? Now, if we do not do this, one can still keep going. But these are being done by us, the human beings. Machine learning is there, AI-based approaches are there, but we are still human beings. We would like to have the satisfaction of having understood something beyond what the program gives you. And in the absence of such understanding, the inspiration for doing something will be only the requirement that we need the drug immediately. But if we have this understanding coming along, or at least we are asking this question to understand, then we have an inherent interest, even when we don't have a hard problem in front. Can I tinker with this molecule so that this could even become better? And can I teach this to the new generation that, look, these are the ways to look for even beyond the program's capability? Because program's capability have given you some answers. We are trying to see how the answer turned out to be the way it is. So this is important. Now, I say this because I don't see this in textbooks. I don't usually see this in workshops because we are all busy targeting a result. After the result is obtained, we have already another problem waiting. So there isn't enough time to look back, sit back and see why the answer turned out to be the way it is. Now, this particular aspect of sitting back and looking things that is done is important in a more general sense, not just in this particular area of drug design, but in research in general. So I might say a couple of sentences about this. It is necessary for any researcher to sit back, and how often one should sit back, it depends on the individual. Maybe if you have lots of results coming in, at least once or twice a year. If that is not the case, in many cases, at least once in 3 years, to forget about everything. Forget about the paper that is being written. Forget about the project that is currently going on. But just to sit back for 10 days without any manuscript in hand, without any computer in hand, but just to think about what was done in the last 5 years, what it all means. Does the result of the last few years have meanings beyond what one has thought? And one should do that by sitting alone or in small groups for 5 or 6 days without worrying about the next referee report or the next correction of the manuscript or the next project that is being written. Often we do not find the time. In fact, I myself feel that I missed out because I did not stop at least every 5 years, not doing anything for 10 days, and then thinking about what is done, not the details of it, but the general picture. So this is what I would like to say even to the young active scientists working in NIPER and those who are just beginning. That is, a certain amount of introspection after having done work for many years would help. It would improve one's work for the coming years. So this is the last of what I wanted to say. And once again, I thank Professor Murthy and his outstanding colleagues for inviting me to inaugurate this workshop. This is obviously something that is absolutely essential. Pharmaceutical and medicinal industry have to come in a big way to solve pressing problems, especially at the current circumstance when we are challenged by nature in the form of a virus. So once again, all the best for the workshop and welcome to the participants. I am glad to say that yes, this will be a success. Thank you.
Very much, sir, for joining with us and addressing all the faculty and student fraternity who joined physically and virtually. And I'm sure that they're all impressed, and also they got so many insights from your talk. Thank you very much for joining with us, and we are looking forward to have you in our campus soon. And thank you once again, sir, for joining. And we are going to be hear more from Narhari Sastry sir and Bharatam sir during the scientific sessions. So with this, we are going to be conclude the inaugural session, and sharp by 10:45, we are going to be start with the scientific sessions. Thank you everyone for joining the inaugural session.
Thank you, sir. It was
that time.
So that's fine, but can I now try to share my slides?
Yes, please.
Because then we will see whether it's working fine or not.
Mm-hmm.
Okay.
Yes,
or should
sir.
I wait for some? I will share it, and then we will start sharp at 10:45. Okay.
Yes, sir.
So, are you able to see me?
Not yet. We are just about to start, but yes,
I have
now
my video on.
yes, sir. Now visible. Okay. Once again, welcome to all in this 3-day workshop on the advanced drug design and medicinal chemistry 2022. So we will begin workshop session, first session, and we are delighted and privileged to have Professor Narhari Sastry as our first speaker. He has done early education from Telangana and Osmania University, and he then did a PhD from University of Hyderabad, and he has done postdoc from a couple of postdocs from a variety of places, and then moved to CSIR IICT in 2002, where he headed the Center for Molecular Modeling, and currently he is the director of CSIR NIST Jorat, and also ACSIR professor in chemistry and life sciences. He has won innumerable awards and recognition. To name a few, Shanti Sarup Bhatnagar Award in Chemical Sciences 2011, National Bioscience Award DBT 2009, and many other, BM Birla Award 2001. And he is a fellow of many academies, National Academy of Sciences, Indian Academy of Sciences, and he is an excellent teacher and mentor, and has guided many students who are now doing excellent in variety of fields. And his major research contributions are in the development of indigenous software for drug discovery, and also contributions to the concept of cooperativity of non-covalent interactions. And there are variety of other applications in QASR, pharmacophore, structure-based drug design, and in modern times he has also made significant contributions to the field of AI and machine learning, about which we are more than eager to hear from him. And I welcome him to this workshop. Sir, please, over to you, sir. Thank you.
Thanks a lot, Vaibhav, for your very nice words, and also I thank you and particularly Professor USN Murthy for giving me this opportunity to be with you. And it was a wonderful day because Padma Shri Professor E.D. Jemmis has started the session with a type of talk which you rarely hear, where he reflected that how somebody has to have a passion to solve big problems. And for the benefit of the participants, I would like to say that if you want to really achieve something, it will take a few decades. And it is not obvious whether you will be even successful or not, but it's very important to ask the right questions, early questions, and also try to passionately pursue your questions despite all odds with the same enthusiasm. I would like to see that if somebody like Professor Jemmis is there, he has contributed to a few fields like Jemmis's rules, which have replaced the Wade's rules in the world scene in the polyhedral boranes, and his generalization of the hydrogen bond red, blue, and no shift is something which is phenomenal, as well as a few other contributions. And it might come slow, but each one of them took a few decades of sustained efforts from a researcher. So I was trained in computational chemistry with Professor Jemmis, along with Professor Bharatam and others. And then I was trying to work in buckyball chemistry, computational modeling, non-covalent interactions. Afterwards, I tried to ask a question that how can we strengthen the computational drug discovery in the country in a way that we will be able to think about newer ways of looking at this computational drug discovery, which will be beneficial both from an academic and an industrial point of view. If you look at the computational drug discovery, this is highly interdisciplinary. You need chemists, you need pharmacists, you need biologists, you need X-ray crystallographers, you need mathematical modeling, you need statistical modeling, and you need people who are experts in dynamics. We need people who are experts in many, many different areas. And all this information is really very important to answer a question. So while it appears to be overwhelming to integrate all the required methods in a given schema or a given way, or in a single platform or in a single group, I think it is highly indispensable. If you do not really integrate all these methods, you may not be able to answer the question. So there are different people, there are different issues. Let us take the three issues that I talked about. There is a huge gap between industry, academia, and educational training. If somebody in NIPER doing their MPharm, they have a particular target wherein they would like to know the fundamentals in a more rigorous fashion. Whereas somebody who is a researcher, like Professor Vaibhav Dikshit, he also would like to know the fundamentals, but also he is more interested in solving the problems of fundamental interest, publish papers, develop technologies, and so on and so forth. And from an industry point of view, people would like to make money from the knowledge that we have. And computational drug discovery will manifest itself very differently in these three different scenarios. One has to see that the computational drug discovery requires a lot of intelligent thinking in different areas of research. And also they will have to realize that this computational drug discovery has to trigger the passion to develop softwares, to develop algorithms, to develop new methods. This is definitely possible in an academic setup, but when you are doing the educational training, you may not have the time. When you are in industry, you also may not have the time. But in the education training, you should have more focus on learning the fundamentals and then how to contribute to the fundamental knowledge. And in industry, you will have different areas where you will have to deliver the product. And also different diseases require different implementations of the computational approaches. You will have one type of an approach for oncology, another particular approach for infectious diseases, and yet another thing for skin diseases, and yet another thing for endocrine diseases or lifestyle disorders. So the way in which you integrate different branches also depends on the disease. Most importantly, people do not have the computational methods which are very easy to implement, so they will have to buy the commercial packages. And they are so expensive, and sometimes they are prohibitive for many educational institutes, academia, as well as industry, because industry also cannot buy all the things. So these are the questions that we have. And we would like to provide a solution that can we have an open source package, as has been discussed in the opening remarks of Professor U.S.N. Murthy, that they are also using the open source packages, and Professor Bharatam Prasad and his group, and particularly Dr. Vaibhav Dikshit, is working a lot on the open source packages. And can we make an open source package which is comparable with the best in the business, the best of the best commercial package? And more importantly, can we position it in such a way that anyone can use it or everyone can use it, irrespective of whether they're in India, abroad, whether they're in small college, big college. They can use it, they can modify it, they can add and improve a particular method. So this is developing this knowledge with the help of everybody and then giving a platform so that they will contribute to that. This is one of the major focus with which we have started this MPDS. It is disease specific so that one can customize the package. So you have an MPDS TB, which is published in 2017, also MPDS diabetes, which is also published. And we have now MPDS COVID, MPDS metabolic disorders, and so on and so forth. So what happens is you have a large number of disease-specific packages or web portals, and finally one is left with a suite of these disease-specific web portals. What's the main purpose of that? The main purpose is to trigger the passion to develop algorithms, to develop programs, and to develop software packages. So the only way that you can strengthen the computational drug discovery and thinking in our country is to trigger the passion to develop our own programs, to develop new algorithms, and to develop eventually the commercial packages. On the other hand, if somebody is really so much addicted, I would use the term strongly, addicted to this commercial packages, they will not be able to do any research in the absence of these commercial packages. That's not going to be good. So we will have to see what is the algorithm, what is the method, what is the procedure, based on which this particular thing is developed. So the purpose is to de-addict the budding researchers, especially.
We request participants to mute their.
Okay, thank you very much. So, is it possible till hello? May I request? Okay, thank you
Yes.
very much. So
We are
is it possible
interrupting this.
for us to de-addict these budding researchers from over-dependence or dependence on these commercial packages? Even if it is not expensive, even if it's a commercial package, and if you don't know what is the method behind that, the use of that will not allow you to improve a particular method that is there. And also, if your institute is unable to pay for that particular year, you may not be able to use it. So I think a computational approach should focus more on the method and methodology, and it should not lead to a situation that it will develop into a full-blown technology in the form of a software where nobody can crack it. So unfortunately, this is what is happening very much. When we were students with Professor Jamis, we used to get many of these computational packages for free from overseas, and people used to encourage us to use it. And when we use their packages, they feel that they are honored about it. There is a quantum chemistry program exchange, and many scientists who developed the package, they used to be so happy if somebody uses their package. So with that spirit, we would like to have a disease-specific web portal, which is called Molecular Property Diagnostic Suite, which is aimed to integrate the open source tools and also develop the open source tools in molecular modeling, in chemical space and biological space, bioinformatics, chemoinformatics, machine learning, text mining. You name any of the packages, we would like to integrate that. I will just quickly go through it, because this particular drug discovery is a very, very challenging thing. When you are having a structure-based approach and an analog-based approach, or virtual screening, ADMET modeling, toxicity, you will have one line of looking at it. But genomics and proteomics have played another very important role. Pharmacogenomics, pathway analysis, what is the side effect, and you have clinical data, and you have something like polypharmacology, and you have many, many other ways of looking at this data. Next generation sequencing has thrown bigger and bigger challenges in working. So we have adopted a Galaxy platform, and I will be very happy to involve anybody who want to contribute to this project. Due to the limited time and also the type of work that we are doing, I just wanted to tell you that in simple words, you can write a program in any language, in any script, anything. This can easily be integrated with the Galaxy interface. And we have done it. And this particular package is available open source, but still it is in the development stage. And we will have to see that there is different modules in MPDS. One is the data library, data processing, data analysis, advanced modules like machine learning, text mining, predictive computing, and multi-scale modeling. And there is also another module which is looking at protein-protein interactions, drug-drug interactions, and disease-disease interactions. And there are certain things which are disease dependent, and there are some things which are disease independent. So far, this MPDS, tuberculosis and diabetes is published. Metabolic disorders was also partly published, but MPDS COVID and MPDS HIV are in the pipeline, and they will be published very soon. So Galaxy is suitable for almost all disciplines in drug discovery, and it's an open source web-based platform for data-intensive biomedical research. So we are using this tool, and this tool already has many different approaches of
It seems
we have left, right? I'm sorry about it. Is it true?
it's okay, sir. Yes,
Okay.
sir. Please continue, sir.
So Galaxy, the tool that is developed in any of these packages can be put into the Galaxy toolbox. For example, if you want to write a new tool in the Galaxy, you can write any program, and this program will be used as a tool, and these tools can be integrated with the host, and then they can be permanently be there in the Galaxy. And if we want, we can also share it with the international community, and anybody who is accessing MPDS will have also access to that. So the beauty is, if you want to write a small program which will improve or add a new computational tool, you can do it. So this will encourage people to write programs, right? Are you able to hear me? Hello?
Yes, sir.
Yeah.
Yes, sir. Please turn on your video, sir.
Oh, you want to see me also. That's good. Okay. Now my video is on. So this MPDS workflow, which integrate the data library, data processing, and data analysis modules. The beauty here is you can have your own workflow, which will be any line of information. For example, I have shown you one workflow here to generate the ID card, which we call it as an Aadhaar card. I will come back to it in our compound library module. So this is a workflow, and everybody can custom design their own workflow based on the tools that are there in MPDS. For example, I would like to have a structure-based approach and then followed by molecular dynamics, and then try to use ADMET, and then I will also try to use the MMPBSA and MMGBSA, and so on and so forth. But maybe Dr. Vaibhav Dikshit may wanted to use the QASR and pharmacophore-based modeling, and he would like to skip anything which is related to structure-based approach. So he can have his own workflow. So these workflows are possible in Galaxy, custom designed workflows, right? So I would like to focus a little bit on the compound library. So basically, chemical space is huge, and people try to say that this is anywhere between 10 to the power of 60 plus to almost 10 to the power of 180. However, the available chemical space is of the order of 10 to the power of 8 or 9. So what to synthesize is the key question. From these number of possibilities of chemical structures, you would like to know which particular molecule to synthesize. Earlier, maybe about 30 years before or 40 years before, how to synthesize was a big question. So the medicinal chemists and pharmaceutical chemists who are capable of synthesizing are essentially limiting the type of molecules that they can use it in drug discovery process. However, current capacity of synthesizing these molecules is so high, so people would like to know what to synthesize than how to synthesize, because how to synthesize may be trivial. So you identify a lead, you optimize it, and you validate it, right? So whether it is for, it doesn't matter whether it is for a drug or a catalyst or an agricultural product or a smart material. So the challenge is to hit the right molecule. So this requires, as has been said, exploring the computational space of the chemical space. I would like to have a small reference or a comparison of molecules with the words and literature from English language. In English language, you have alphabets, whereas in molecular space, you have elements. You have words in English language, you have molecules here. And similarly, you have sentences, you have supramolecular assemblies. And here you have a huge chemistry. The interactions are essentially unlimited. So you can see that you can create infinite number of molecules from a finite number of elements or fragments. And we can also look at these molecules as fragments, rings, linkers, scaffolds, and substituents. This is another way of doing it. And people will try to see that the bioactivity is located in some part of this molecule. And then there's a lot of work that has been done in medicinal chemistry, pharmaceutical chemistry, drug discovery. But it's also important to know that even a very, very small difference will make a huge difference in the biological activity. I just wanted to tell you that there is a huge difference between water and methanol. The difference is only you replace the hydrogen by a methyl group, and if somebody consumes methanol, it is highly toxic. There's lots of spurious deaths, whereas ethanol is not that toxic, whereas water is not at all toxic. So you have large number of cases where a very small change will lead to a huge change in the biological activity. You don't have to look at the substituents. Even the mirror image might have a huge biological activity difference. That's why this chiral synthesis is also very important. Notwithstanding all these things, similar molecules are expected to have similar properties, and many approaches are also made based on this. So I will try to tell you that in MPDS, we try to feel that every molecule is unique, and I always try to compare. Earlier, I tried to compare the molecules with words, but I would like to actually compare the molecules with human beings, because every molecule is unique and it is destined to do something in biological space. Whether you administer a molecule in your human body, and it will do wonderful things. And similarly, human beings also will do different things. And we call that every molecule is unique, and then we will have to find the properties of that molecule. This is the reason why we call it as the origin of this term molecular property diagnostic suite is to essentially evaluate and assess what is the nature of your molecule, what is the worth of your molecule, what is the problem of your molecule, what is the potential of your molecule. You have to thoroughly diagnose the entire profile of that molecule. That's the reason why we have called this as molecular property diagnostic suite, where every molecule is given a unique ID, which I would like to call it as Aadhaar card. Not only we call it as we have published this term Aadhaar card associated with MPDS unique ID, where you will be able to provide every possible information about that particular molecule in the Aadhaar card. That will give you a huge chemical space. You can think about 10 to the power of 60 chemical space, where each molecule can have hundreds of properties. Actually, if you see Professor Bhartam Prasad, he will say that there are about 5,000 molecular descriptors. So each molecule has 5,000 descriptors. So it's a huge space that we are talking about. So the data is very high. So there's a lot of scope for us to see how you get the information, knowledge, and predictive ability from the data. So there is a lot of scope for machine learning approaches. There is a lot of scope for deep learning approaches. And I would like to see that we have published quite a few papers in the last couple of years, which I'm not going to discuss about you. Because those of you who are interested, they can go through from our website or from internet what are the things that are published from our group. So they will know that there is a lot of scope for AI and machine learning approaches to be applied to chemical space. So MPDS compound library has a unique set. First time we will try to have a structurally well characterized group, which we call it as a class, and then there's a cluster. And from there, we will be able to categorize the molecules in terms of classes and clusters. And while we published it about a few years before in 2007, we are now reviving it, and we will try to develop a series of disease-specific web portals. As I said, we have MPDS TB, MPDS diabetes, MPDS COVID and HIV and metabolic disorders are in place. All these suites of MPDS programs will be combined into one galaxy, where you will be able to talk a lot about chemical, biological space, chemical information, chemoinformatics, and drug discovery tools. And I think there is a lot of scope for that, but my idea is to introduce you to this MPDS and tell you that there is a lot of scope for AI and machine learning. And Galaxy interface for an MPDS portal, it manages all computational tools in Toolbox, and the job manager deals with the details of executing tools. And there is a web interference, provides Galaxy through a web browser and provides an abstract interface with a model for working with the data sets. Actually, this is one of the contributions from Professor Bharatam's place, where probably Vaibhav was
on the Sastri sir's side. So, but he is online with me on WhatsApp call, and he would like to conclude with few sentences. So over to him. You will be able to hear him.
Please turn on your video.
Really unfortunate that our institute has been undergoing some major issues with the power and the network. So what I want to say is this molecular property diagnostic suite is essentially designed to see how exactly a person can develop a tool and then use it in an academic setup where their dependence on the commercial tools will be less. So I would like to share my PPT as a file along with Professor Vaibhav Dikshit will give you. And I'm extremely sorry for this very unfortunate situation. And then hopefully we will be able to meet sometime. And then I request, I am sorry for this, and then I will be making my slides available to all of you. If there is any question or something, I will be able to answer online, or if you ask me, I will be able to answer you right now.
Yes, sir. We have not received any question online, but here those who are online with us on the Microsoft Teams, if there is a question, sir is listening.
So thank you very much, Vaibhav. If there is no question.
Yes, sir. Sir,
please convey my regards. Yeah.
No, sir. You continue, sir. Please.
Vaibhav sir, can you please turn on your video?
Please convey my regards to Professor Coutinho. Right. And thank you very much. And I'm very sorry for this bizarre thing, which usually does not happen with me. But today there is a problem with the connection, like power collection mainly. Okay.
No problem, sir. We are very much privileged to have you, and you could spare your time from your busy schedule. And I'm definitely sure that students who were listening, they got not only inspirational advice, but also technical details that they could see and how open source should be and can be incorporated so that it is available to everybody. That definitely message has percolated, and we are feeling excited about this. Thank you so much, sir. Okay, now we already have the next speaker with us. Professor Coutinho, can you hear me? Hello.
Please. Okay. Can you hear me? Am I audible?
Yes, sir. Yes, sir. Yes, sir. Can you turn on your video, sir?
Yeah, 1 minute. Just give me a minute.
Okay, sir.
Am I visible?
Yes, sir. You are visible. Sir, if you can share your slides, then I will introduce you.
Yeah.
Once again, welcome to everybody. So we have Professor Ivan Coutinho with us. He is a professor of pharmaceutical chemistry at the BCP Mumbai, and he has done his education from Mumbai, and he has received innumerable teaching and research awards, resident scholarship, residential school on medicinal chemistry, Drew University, a career award for young teachers of the AICTE, and he was nominated by Vice Chancellor to the Senate and Students' Council of Bombay University. And he has been also awarded with the Professor J.G. Kane Memorial Prize and many others. So his main expertise is in the area of computer-aided drug design, homology modeling, docking, pharmacomodeling, QASR, and also molecular dynamics, synthesis of chemical entities, and he specializes in the analysis and interpretation of NMR of small as well as large molecules with 1D, 2D, and multidimensional NMR methodologies. And we have had the good fortune to have him. So over to you, sir, for your presentation.
Thank you, Dr. Vaibhav, for this nice introduction. And thank you for this invitation to talk at ADDMC 22. Okay, my talk will be on QASR. And let me say at the very beginning that I'll be talking about the elements of QASR. So this is going to be some very basic principles on QASR. And I want to talk to those who are not the uninitiated in QASR, people who have no expertise and no knowledge about QASR. I'm trying to initiate them into this very exciting field. I know that in the audience, there may be people who are experts in QASR, so kindly bear with me, okay, about that. I'm going to avoid talking about my own research on QASR, about advances in this field. Okay, so let's start with the introduction. So what is QASR basically all about? QASR tries to draw a mathematical relationship between biological activity and the physicochemical properties or the structural properties of this molecule. So I want to develop a mathematical model. Now, though I am stating here that we are going to talk about a model between biological activity and physicochemical properties, we do not restrict ourselves only to biological activity as the endpoint. We could also develop models for toxicity. For each one of the ADDMC properties, we could build models for absorption, for metabolism, etc., etc. Okay. Also, we could have QSPR, quantitative structure, property relationships, or more important, pharmacokinetic relationships out there. Okay. So we can have several endpoints. But in this lecture, I'm going to talk about the pharmacological endpoints. Okay, the biological activity as a relationship between the physicochemical properties of molecules. Now, where do we get these physicochemical properties? These can be calculated. Okay, we have a lot of mathematical equations which enable us to calculate a variety of physicochemical properties. And I'm talking about these physicochemical properties in my lecture. Or we could also do experimental measurements of these physicochemical properties. Most of the times we have an admix of the two. We calculate some of these properties, and some of these properties actually come from experimental measurements out here. Okay, so we are developing a mathematical model. This mathematical model must be evaluated, must be validated. And once we have this mathematical model, okay, we can then use this mathematical model for prediction. Okay, so we were going to predict the activity of some, I would say, unknown compounds. Now, what do I mean by unknown compounds? Okay, compounds which have not been used in building this mathematical model. Okay, so these are compounds which are not part of the building of the mathematical models. We can predict their activities using this mathematical model. Okay, so let's talk about these different elements that are there in the QASR. First, about this mathematical model, then a little bit about the evaluation and the validation of the model, and finally, if time permits, something about prediction of QASR out there. Okay, so the QASR, okay, was originally conceptualized by Professor Corbin Hansch. Okay, Professor Corbin Hansch. Now, Professor Corwin Hansch actually worked all his life in a very small college in California. It's a community college in Pomona, in a small, hamlet in California. It's called the Pomona College. From there, he developed all his ideas and expanded it to a very great level. So now, if you are trying to talk about the biological activity of molecules, then there are two aspects that we must take into consideration. First is the pharmacokinetic aspects. The pharmacokinetic aspects deals with the journey of a drug from the point of entry, from the site of administration to the site of action. Okay, this site of administration generally will be the gut, if this is a solid dosage form like a tablet or a capsule, and the site of action could be, for example, could be the heart if you are trying to treat hypertension. Okay, the journey from the site of administration, from the duct to the heart, okay, from the gut to the heart, involves a lot of elements inside it out here. It's a Herculean task because there are many barriers that the drug must encounter in order to get on from the site of administration right into the site of action. And the site of action, basically, it is then going to interact with a particular receptor inside the heart out here. So after it has reached the heart tissues, then it interacts with a particular receptor. Let's say we argue and say this is the beta adrenergic receptor, and there it must now modulate or silence the receptor. And this part is basically the pharmacodynamics, the interaction of a drug with a receptor in order to stimulate it or to silence it is pharmacodynamics. So if we are trying to explain biological activity, our explanation must involve both pharmacokinetics and pharmacodynamics. And pharmacodynamics involves basically absorption, okay, and distribution. And as I told you, this is a Herculean task. Okay, right, for a drug, there are many, many barriers which the drug must be able to encounter and pass through, right, in order to reach the site of action. Primarily, okay, this transport or this journey from the site of administration to the site of action is critically dependent upon lipophilicity. Now you think of all the barriers that a drug generally meets when it has to move from the site of administration to the site of action. First is there is the GI tract. Okay, there are a lot of these membranes which the drug must pass through these membranes and then exit the membranes, dissolve in aqueous media. And there is this always moving from membranes to aqueous media, back to membranes and back to aqueous media before it is able to reach the receptor and interact or stimulate the receptor. And this passage from the site of administration to the site of action is dependent upon the lipophilicity. As I told you, it encounters barriers which are of two types, basically lipophilic barriers and aqueous barriers out here. Okay, so you must actually have a balance, okay, a balance of lipophilicity and hydrophilicity. Okay, because as you see in this journey, there are membranes which are lipophilic and there is the aqueous medium, okay, which is hydrophilic out there. Okay, so a drug must have lipophilic characteristics in order to be successfully absorbed and distributed and reach the site of action. At the site of action, when it encounters with the receptor, there the electronic effects of the drug come into play and the steric effects come into play. Okay, so now let's see, how do we account for these properties, the lipophilic property of a molecule, the electronic properties of a molecule, and the steric properties of a molecule. At that time, okay, nothing was known about how to express the lipophilic nature of a molecule. When Hansch had introduced his idea about QASR, there was no methodology or there was no idea exactly about how does one express the lipophilicity of a molecule. And it was he who introduced this partition coefficient. Okay, so today what we use very routinely and take very much for granted when we want to measure the lipophilicity of a molecule, we actually do this octanol water partition coefficient experiment. But it was actually Hansch who introduced this idea of partition between octanol and water, one octanol and water, as a measure of the lipophilicity of the molecules. Okay, I'll talk a little more about this octanol water partition coefficient and how it expresses the lipophilicity of a molecule. At this point of time, let me tell you that the octanol water partition coefficient is not the only way to talk about the lipophilicity of the molecules. More about that a little later on. Now, coming down to the electronic effects. To express the electronic effects of a molecule, Hansch used the Hammett's constants. And we'll come to this a little later on. And to express the steric effects of a molecule, okay, Hansch used the steric effect as dictated by the Taft's parameter. Okay, so what is Hansch logic? Hansch logic is that if you have to talk about or build a model for the biological activity of a molecule, you must account for both the pharmacokinetics and the pharmacodynamics. The first attribute, the pharmacokinetics, is critically dependent upon the lipophilicity of the molecule. And to account for the lipophilicity of the molecule, we use this octanol water partition coefficient. To express the pharmacodynamics of the molecule, both the electronic effects and the steric effects are important. And these can be expressed in terms of the Hammett's constant and the Taft's constant. So more about this as we go along. But let me talk about this lipophilicity. Okay, the most important thing is basically, okay, Hansch believed that there must be a free energy relationship between lipophilicity and biological activity. In fact, the Hansch model is nothing but a linear free energy model. A linear free energy model. That is the Hansch's model of QASR. And therefore, we must remember that, every element that we are trying to use in developing a QASR model must be associated with the free energy of the system out here. This is very, 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 very important. And we know that when we are trying to express QASR in terms of lipophilicity of a molecule, we know that basically there exists a free energy relationship between lipophilicity and activity. Okay, so likewise, there must also be a free energy relationship. Okay. Likewise, there must also exist a free energy relationship between the electronic effects, that is the Hammett's constants, and a free energy relationship between the steric effects and the activity. Okay, so likewise, we must have also for the electronic properties, okay, a free energy relationship with the activity, and for the steric properties, we must also have a free energy relationship with the activity. In other words, okay, whatever terms or parameters or variables we are using in order to develop a QASR equation, we must be careful that all our parameters, all our variables, okay, which we are trying to say that accounts for the activity must have a free energy relationship with the biological activity. This is very, very important in QASR. So let's look at about lipophilicity. We all know this experiment very well, and we say that the partition coefficient is basically nothing but a concentration of a compound in water divided by a concentration of the compound in the aqueous phase. This equation up to this point is good for a non-polar molecule. for a non-polar molecule. The concentration of the compound in octanol divided by the concentration of the compound in the aqueous phase. If I take this ratio, it is a good equation to express the partition coefficient for a non-polar molecule. However, when we have polar molecules, okay, for example, most of our drugs are basically weak acids or weak bases. Okay, or weak bases. And these basically will ionize at physiological pH. The weak acids and weak bases, which are our drugs, basically are going to ionize at this physiological pH of about 7.2. And if they are going to ionize at physiological pH, then what has happened is the ionized forms, okay, the ionized forms of the weak acid or the ionized forms of the weak bases then will have an extra solubility in the aqueous phase. So these forms are basically going to dissolve into the aqueous phase and are going to contribute, okay, to a higher concentration of the compound in the aqueous phase, okay, more than simply being accounted for the non-ionizable form. The non-ionizable form also, okay, the non-ionizable form of the weak acid and the weak base also dissolves in water. Intrinsic solubility. However, okay, when they ionize, we have this extra solubility coming from the ionizable forms. And to account for this, we have this term 1 minus alpha, where alpha is basically the degree of ionization. Okay, so we have to be careful when we are measuring the partition coefficient of weak acids or weak bases. Okay, we must also use this term 1 minus alpha to account for the solubilization of both the unionized forms in the aqueous phase as well as the ionized forms in the aqueous phase. Okay, so let's look at what are these values of P that we can get. Okay, so we can get P less than 1, okay, and we can get P greater than 1. Okay, so when P is less than 1, it simply means that, okay, our molecule is more soluble in the aqueous phase. And if P values are greater than 1, we simply know that a molecule is more soluble in the octanol phase. Okay, when P is equal to 1, we have basically equal solubility in the octanol phase and the aqueous and the aqueous phase. Okay, so now remember that this is very critical because the ability of a molecule to move, okay, from the site of administration to the site of action is critically dependent upon this P value. If the molecule is very, very lipophilic, it will get sequestered in the lipophilic phases in the body. It will just get bound in the membranes, and it will not move from the membranes into the aqueous phases. On the other hand, if a molecule is very hydrophilic, then the molecule will solubilize in the aqueous phases and not dissolve or not penetrate into the membranes, which are lipoidal in nature. And therefore, this property is very important for when we are designing compounds. Okay. You must appreciate this property a lot because most of the times a lack of activity is simply because our molecules are either too lipophilic or too hydrophilic. And designing a molecule which has a right balance between hydrophobicity and lipophilicity is not a trivial issue. Okay, it requires a lot of intelligence, it requires a lot of hard work, it requires a lot of design efforts in order to be able to do this. So I hope I'm emphasizing a lot about when you're making molecules, take care of the lipophilicity. See that you are able to design molecules to strike the right balance between lipophilicity and hydrophilicity. Otherwise, you're bound to have a failure in your hand. Okay, now the relationship between lipophilicity and activity is not very simple. Actually, many times we see a non-linear relationship out here. For example, I take one example of ethers and I look at the anesthetic activity of the ethers. And if I were to plot the anesthetic activity on the y-axis versus the lipophilicity expressed as log P on the x-axis, then I see that the relationship follows a curve. This is a parabolic curve. This is a parabola curve. Now, what does it mean? As lipophilicity increases, okay, as lipophilicity increases, you begin to see that activity increases. So this point, you have a more lipophilic molecule than the point here, and here you see you have an increase. You have an increase in the activity. So as we go on increasing lipophilicity, you have a commensurate increase in the activity. But here you reach a point. Okay, at this point of lipophilicity, you have the optimum in the activity. You have an optimum in the activity, and a further increase in lipophilicity, actually you begin to see you're going to get diminishing returns on the activity. The activity is actually going to fall down. So this part is actually where increasing lipophilicity causes a decrease in the activity. So there is an optimal inside the activity. So now if I were to write a mathematical model for the activity and the logarithm of the partition coefficient, you have this relationship. You have this relationship out there. You have a non-linear relationship. Okay, so this is your non-linear term, and this is your linear, and this is your linear term. So what I'm trying to say is that biological activity of many compounds have a very complicated relationship to the partition coefficient out here. Okay, so for many compounds, you have this what is called as a non-linear relationship, which is composed of a parabolic term and a linear term out here. And these numbers are basically showing you how the parabolic term contributes to the activity and how the linear term contributes to the activity. Notice that the parabolic term has a negative coefficient. More about this a little later on. However, the linear term has a positive coefficient. There is significance in these values and their signs. More about this a little later on. So what I'm trying to emphasize is about lipophilicity and biological activity, that it could be a very complicated non-linear relationship out there. Okay, so what does log P do? Log P is a measure of the lipophilicity of the entire molecule. It tells you how the entire molecule distributes between octanol and water. Okay, but many times we are more interested in, for example, if I have a substituent, I would like to know how this substituent influences the lipophilicity of the molecule. For example, let's say I have a core structure, and this core structure could be an imidazole, ring. Okay. Okay, and many times I would like to know, for example, how a substituent at this position, this is the fifth position, actually alters or changes the partition coefficient of that molecule. Would it not be nice to know, for example, a methyl group, then if I have an amino group, how do I can relate to the changes, the methyl group and the amino group, how do these change the lipophilicity of the molecule? So what we are trying to understand is substituent constant. How do substituent constant affect the lipophilicity of that of the molecule? Okay, so Hansch came up with this idea of substituent constant. Okay, and what he said, for example, okay, this the substituent constant to the lipophilicity given by pi x is given by the partition coefficient of the molecule with the substituent minus the partition coefficient of the molecule which doesn't have the substituent. So let's say I have a core structure here, some core structure. Okay, as my example, this is imidazole out here. I have some substituent X here. And then my other molecule is simply the core molecule. And at this position, there is a hydrogen where the substituent is attached. For example, if the substituent is attached at the 5 position on this core structure, my parent compound is there's a hydrogen at these 5 position. Then I measure the lipophilicity of this molecule. Okay, the partition coefficient of this molecule, and I measure the partition coefficient of this molecule. And when I subtract the two, the logarithm of the partition coefficient of the molecule, which has the substituent, minus the logarithm of the partition coefficient of the molecule, which has a hydrogen at that same position, I will get the contribution of the substituent to the lipophilicity of that molecule. And here is what a medicinal chemist can use to great advantage. So if I know how substituents alter the partition coefficient, then when I want to modify the lipophilicity of the molecule, I can get an idea of what sort of substituents do I need to put here in order to change my lipophilicity to the extent that I want. Either I want to elevate the lipophilicity or I want to bring down the lipophilicity, then I know what type of substituents will help me to increase or to decrease the lipophilicity from these values. And here are some values for different substituents out here. For example, now this is very, very a little bit complicated out here. Why? Because, okay, the effect of a particular substituent on the lipophilicity is dependent upon what is this core structure. Okay, for example, if this core structure is an aliphatic chain, okay, and if I have some substituent on this aliphatic chain, and if my core structure is aromatic, and I have the same substituent X attached to the aromatic ring, the contribution of X to the lipophilicity of the molecule and the contribution of X to the lipophilicity of this molecule is not going to be the same. Okay, so when we are talking about the substituent constant, the pi X, the substituent constant, okay, to the lipophilicity of different groups X, we must ask ourselves, what is this core structure to which X is joined? Okay, this is important. And here you begin to see, okay, when your X's, these are your X's, are attached to aliphatic groups, these are the values that you would get. When your X is attached to an aromatic group, these are the values that you will get. For example, if methyl is attached to an aliphatic group, the contribution of methyl to the lipophilicity, and when it is attached to an aromatic group, the contribution to the lipophilicity is not much different. However, when I look at methoxy, and when methoxy is linked to an aliphatic group, I see that its contribution to the lipophilicity is something like plus 0.47. But when the same methoxy group is attached, for example, to an aromatic ring, for example, like a benzene ring, okay, to a benzene ring, then its contribution to the lipophilicity is absolute. In absolute values, it is only 0.02. But more importantly, the contribution is plus here, while the contribution is negative here. It completely changes, okay, what it does to the lipophilicity of the molecule. Very amazing. Another example is here. Okay, when I have a chloro group, the contribution of the chloro group, okay, to the lipophilicity of an aliphatic group is 0.39. And when the same chloro group is attached to an aromatic substituent, its contribution is 0.71. In this case, the contribution is both positive and positive, but in absolute numbers, you can see almost double. Its contribution to the lipophilicity is almost double. Here is another amazing molecule. The fluoro on an aliphatic, its contribution, its pi X is minus 0.17. And when that same fluorine atom is attached on an aromatic substituent, its contribution goes from minus to plus, and the absolute value remains more the same. More importantly is this sign, what it does to the lipophilicity, whether it increases or decreases the lipophilicity. Okay, so you have tables for this for a large number of substituents, and you can also have tables for these substituents on different types of core structures. Okay, Hansch has actually a huge number of tables. During his entire lifetime of work, he spent a lot of effort in developing such type of tables for a variety of substituents, from very simple substituents to very complicated substituents when they are attached to different core structures out here. And for whatever molecule you are going to design during your work, I would recommend that you would definitely find them in one of Hansch's tables. Okay, there's a compilation. There are books today, okay, databases today to tell you the contribution, okay, the pi values for different substituents on different core structures out there. Okay, so I've given you an inkling about lipophilicity and the importance of lipophilicity in the biological activity and how we can account for lipophilicity in terms of the partition coefficient. Remember that I told you that, okay, the lipophilicity is basically pharmacokinetics, and the pharmacodynamics of the molecule, okay, involves the electronic features plus the steric plus the steric features out here. Hansch, when he originally developed his QASR equation, he took into consideration only lipophilicity and electronic properties. So this is lipophilicity, and this is the Hammett's constant, which accounts for the electronic properties of the molecule. Here is an analogous equation. Here is an analogous equation where the Hansch's equation now is in terms of the substituent constant. In place of the partition coefficient of the molecule, he replaces it with the substituent constant that we saw in an earlier slide. So we have two formulations of the Hansch's equation. One's in terms of the substituent constant and the other in terms of the partition coefficient of the entire molecule. So now you can ask me, why did Hansch omit steric features? Yes, his early equations, okay, focused on lipophilicity and electronic properties. And many times he was not able to get very significant mathematical equations. And later on, he realized that something was missing from this equation, and therefore he added the steric features out there. Okay, so his later equations, okay, I'll just draw. Here is his final equations that he developed. Okay, so in terms of the substituent constant, you have these two terms expressing lipophilicity, and then you have these two terms to express pharmacodynamics. This is PD, this is PK, and for pharmacodynamics, you have the electronic properties in terms of the Hammett's constant, and you have the steric properties of the molecule in terms of the Taft's constants. Okay, so now now that you know about lipophilicity, okay, let me say a few words about this Hammett constants and this Taft's constant. What is this Hammett constant sigma? Okay, just like we have pi of x, we also have sigma x. Okay, that is telling you the electronic properties of a particular group, of a particular substituent. Okay, let's say we have benzoic acid. Okay, we have benzoic acid. You know, benzoic acid is going to ionize as the benzoate ion like this out here. And there would be an equilibrium constant. Okay, that means there would be a certain amount of this in solution, that is the ionized form, and there would be a certain amount of the unionized form in solution, and there is an equilibrium between the ionized and the unionized form. Now, if I have a substituted benzoic acid, for argument's sake, let me say that this X is the nitro group at the 4th position. This is 1, this is 4. So I have para-nitrobenzoic acid. And para-nitrobenzoic acid would now ionize as the para-nitrobenzoate ion plus H out here. So my question is this. Okay, when I look at para-nitrobenzoate ion, what is this? Is this higher than simple benzoic acid? Is the concentration of the para-nitrobenzoic acid higher than the concentration of unsubstituted benzoic acid? And to address this, basically we can look at the ionization constants of these two groups, of the parent benzoic acid and the ionization constant, or the equilibrium constant equilibrium constant of the substituted benzoic acid. And if I were to take the logarithm of the equilibrium constant for the substituted benzoic acid, this equilibrium constant, divided it by the equilibrium constant for the parent benzoic acid. So this O is for the parent benzoic. If I were to take this ratio, then I get this number sigma. This sigma tells me how does X influence the extent of ionization, whether this nitro group is going to increase the ionization of the benzoic acid or it's going to suppress the ionization of the benzoic acid. All of you who are in chemistry know that the nitro group is a powerful electron withdrawing group, and because of its inductive effect, it actually stabilizes the para-nitrobenzoate ion. Okay, so the nitro group actually causes more of the ionized form to exist in solution when we reference it to the parent benzoic acid. On the other hand, if I were to put an OH group, because an OH group is electron releasing, what it does, it suppresses the ionization of the para-hydroxybenzoic acid. So this is going to be less than the parent benzoic acid out here. So this extent of how much a group, OH or a nitro group, the X group influences the ionization, increases or decreases an ionization, will be given by this value sigma. Okay, so we saw different values for pi. Okay, I showed you different values for pi. Now Hammett has also produced different values for sigma. Now I do not have, unfortunately, I do not have a table for the different values of sigma. I'm sorry out here, but you can look at tables for the Hammett's constant and you can get an idea, just like I showed you for pi of x. Okay, you can get values of sigma of x for different type of groups, how it influences ionization. And remember, all of these values will also be signed, will have a plus sign or a minus sign. And this sign to the values, for example, sigma of nitro group may be something like plus 2.5. Okay, don't believe me exactly, I'm just giving you some arbitrary number. Okay, so this plus tells you basically that nitrobenzoic acid, okay, that the nitro group actually promotes ionization. On the other hand, if I have sigma of OH, this will turn out to be something like minus 0.32. Don't take these absolute values. I'm just giving you examples out here. This minus tells you basically that the hydroxy group suppresses ionization out here. So just as you see that X has a sign here, some of them have a positive sign, some have a negative sign. Sigma X will also be signed, will have an absolute number and also be signed. And that sign tells you whether it suppresses ionization or it promotes ionization out here. So there are tables available in the literature. Again, some of these were also compiled by Hansch, but most of them were developed by the original scientist, that is Hammett. That's Hammett out there. Okay, now coming down to the, now I told you about sigma. Now, what about this Taft's constant, which is an expression of basically size or shape of that molecule, basically expressing steric properties, the steric attributes of this molecule. And the steric attributes basically kick in when a drug interacts with the receptor. Okay, for example, if this is the active site, if this is the active site or the binding site, this, okay, with this size and shape. And if this is the shape of the active site, then very obviously, even though this molecule may be able to penetrate the membrane, it may have a right balance between lipophilicity, enter inside the cell, it may not be able to interact with the receptor because the receptor size, the active size is very, very, very small, okay, of the receptor. And this molecule has a size and shape that is larger than the active size and shape of the receptor or the volume of the receptor pocket out here. So we must be careful that we must be able to account for this property also. So a molecule may have the right lipophilicity, it may have the right electronic properties to interact and stimulate the receptor. However, if it doesn't have the right steric attributes, it will not be able to sit inside the receptor cavity and stimulate or silence the receptor. Let me use the word modulate the receptor. So modulation could be both an enhancement in the activity or a silencing of the activity out here. So how do we get an idea about the steric attributes of a molecule? One of the ways in looking at the steric attributes of this molecule was first expressed by Taft. Okay, Taft says that, you know, the effect of the size of a group, okay, can be looked about if we were to measure how this group X influences the hydrolysis of an ester. Okay, so you can get an idea. For example, if X is small in size, like a methyl group, and if X is very large, like a tertiary butyl group, okay, like a tertiary butyl group, then you know that the tertiary methyl group would actually hinder, because of its size and shape, it would hinder the rate of hydrolysis of this ester. On the other hand, a small group like methyl, okay, for this is basically methyl acetate. It would hydrolyze faster than methyl, okay, this tertiary butyl derivative out here. So by looking at the rate of hydrolysis of XCOMe and the rate of hydrolysis, K is the rate of hydrolysis of this ester, CH3COMe, this is the reference, okay, then I can get an idea about how X, whether it facilitates hydrolysis or whether it hinders hydrolysis. And I will get a number for this. If I take the difference of the logarithm of the rate of hydrolysis of the substituted ester to the parent acetate, to the parent methyl acetate, if I were to take the difference of the logarithm of the rate of hydrolysis of these two compounds, then I can get an idea about how X, the shape and the size of X influences the hydrolysis, and that would be reflected in this number ES. So here are some values for EX. Okay, since our reference molecule is CH3COOMe, so if I were to put here also CH3, then basically this will turn out to be 0. Okay, turn out to be 0. So the reference is basically the methyl is 0. Now anything greater than methyl would actually decrease the rate of hydrolysis, as you can see here. The ethyl, the N-propyl, the isopropyl, the N-butyl, the isobutyl, all of these are groups which are larger in size than the methyl, and you can see the influence on the hydrolysis. They retard the hydrolysis of the ester. Here is the value for quite a large group, a cyclopentyl group. Okay, the cyclopentyl. Now, groups which are smaller in size, than the methyl, would actually promote hydrolysis. So you can see we have the largest value when X is basically hydrogen out here. So these values basically get you an idea about the size and shape of a molecule out here. Okay, so now let's go back to this Hansch's equation. Okay, so we saw these terms are an expression of the pharmacokinetics. These terms are an expression of the pharmacodynamics. So we use lipophilicity for pharmacokinetics, and our first expression of lipophilicity was log P. Then we use electronic properties for the pharmacodynamics, and our expression for the electronic properties was the Hammett constant. And then we use the steric size and shape of a molecule out here. Okay, steric for steric attributes. And we use basically the Taft's constant to express the size and shape of the molecule. However, there are umpteen ways. If I want to talk about lipophilicity, the log P is not the only way to talk about lipophilicity of the molecule. If I want to express the electronic properties of the molecule, the Hammett's constant is not the only way. Likewise, for the steric attributes of a molecule, the Taft's constant is not the only way. We have so many ways of expressing the lipophilicity, the electronic attributes, and the steric attributes of that molecule out. And I'm going to basically show you. See, look at lipophilicity. If I want to talk about the lipophilicity of the molecule, the log P is one way, which was originally used by Hansch. But the log D, the distribution coefficient, the retention times on an HPLC and on a TLC can also be used to express the lipophilicity of the molecule. Lipophilicity of the molecule can also be expressed in terms of solubility. Definitely. And for solubility, you can have so many ways to measure the solubility, the molar solubility, the molar fraction solubility, the activity coefficients, the Hildebrand solubility parameters. All of these are expressions of the solubilities, and solubility itself is a method of being able to account for the lipophilicity of the molecule. So what I'm saying that lipophilicity, we have so many ways. I've listed only 4 or 5 of them, but there are many other methods of accounting for the lipophilicity. Likewise, the electronic attributes of the molecule. Hansch used the Hammett's constant. However, we can also have the dipole moment to talk about the electronic attributes. You can also talk about the ionization constant, the pKa, also to express the electronic attributes of a molecule. You can use hydrogen bonding parameters to express about the electronic properties. And you can use a whole set of quantum mechanical properties in order to account for the electronic properties of the molecule. You can use delocalizability, polarizability, homo-lumos energies, charges, the charge distribution of the molecule. All of these are basically expressions of the electronic properties of the molecule. Likewise, when it comes down to the size and shape, we saw that Hansch used the Taft steric parameter to express the size and shape of the molecule. The molar refractivity, the paracord parameter, the Forloof's parameters are all expressions of the size and shape of the molecule. Constitutional attributes like the number of atoms, individual atom types, the number of rings, the molecular weight of the compound, the different types of bonds, okay, the different types of bonds. All of these are also fairly good ways to account for the steric properties of that molecule out here. And then you have the topological values. Okay, the Wiener index, the Randish index, the Kyer and Hall index, the Balaban index, whole number of indices. Okay, these are called as the topologic, which are an expression of the size and shape of the molecules, can also be used to speak about the size and shape of the molecule. Geometrical parameters like the moments of inertia, which is very popular in QASR today. Okay, solvent accessible molecular area, also very popular in QASR today. Molecular surface area, also very highly used in QASR, are all expressions of the size and shape of that molecule out here. So what I'm trying to tell you now, why I'm getting you all of these. Okay, when I'm developing a QASR equation, okay, I can replace, okay, I can replace in my QASR equation with the biological activity, I can have other terms for the lipophilicity, as I told you. Okay, other terms for the lipophilicity. In place of log P, you can have a QASR equation where you have basically the RF values or the RM values, or even the Recur's constants F out here. So you can have basically F appearing in these equations. Okay. In this equation, you can basically have the Recur's constant appearing out here. Okay. In place of the Hammett's constant, the electronic properties, you can have in place of this any one of the electronic properties that I talked about. You can have dipole moment appearing in that equation. Okay, you can have the dipole moment that is appearing inside this equation in place of sigma. For the steric attributes, you can have any one of these coming to you can use the Wiener index, you can use the Kyer and Hall indices, okay, the Kappa indices, you can use any one of these to account for this. So today, when we talk about the QASR equation, we have simple QASR equations, we have very complicated QASR equations, and you have a lot diversity in the type of QASR equations out here. Now, one of the things that may come in your mind, I'm trying to develop a QASR equation. Which are these parameters that I need to have inside my equation? As I told you, what are these parameters? These parameters are expressing lipophilicity, electronic properties, and steric properties. These are basically referred to as the parameters or as the variables of my QASR equation. So let me go back to my QASR equation. Okay. These are referred to as the variables of the QASR equation. And you can have any number of these variables, okay, that can crop up in your QASR equation out there. Okay, so the most important thing is okay, which are these variables that are able to account for the biological activity very accurately is the ones that will appear in your QASR equation. Here is an example of a Hansch equation. Okay, these are an equation of beta halo. So X is chloro, bromo, fluoro, beta halo, and we have beta substituted aryl. So this is the alpha, this is the beta carbon atom. So at the beta position, you have basically a halogen, and then you have a substituted phenyl ring at the beta position. Okay. The equation for the QASR equation or the Hansch equation for the biological activity of these compounds. What is the biological activity of these compounds? Is the adrenergic blocking activity of these compounds actually is related to the Hamilton substituent constant for the group at Y and the Hansch substituent constant for the group at Y, okay, and the Hamilton constant for the group of X. A very simple QASR equation out here. Okay, so now let's look at this QASR. I want to say a few words about when I get this QASR equation. There is a lot that I can do with this QASR equation. So this number tells me how much does pi of Y contribute to the biological activity. This is how much does the substituent constant of I contribute to the biological activity. And this number minus 1.59 tells me how much of the Hamilton's properties of this X contributes to the biological activity. Okay, there is a minus value for this number and a plus value for this number. That means if I increase lipophilicity, okay, I can get a commensurate increase in the biological activity. However, must be careful with this term because this has a negative term. So what type of groups at X basically will contribute to the activity? That X must be negative. Okay, that X must be chiefly electron donating groups. Okay, electron donating groups. So if I have electron donating groups basically here, okay, electron donating groups are basically here, then I can get an increase in the activity. However, if X is electron withdrawing, then what has happened is then there will be a fall in the activity. So what I'm trying to just give you an idea that, okay, this has a lot of implications in drug design. How much do I need to make molecules with an increase in lipophilicity? And when I'm putting substituents on my molecule, what sort of substituents do I need to put in that? So for an analysis of this equation gives me good ideas in making new molecules with the requisite attribute with my intention to increase the activity. If I just do this randomly, then I can either get an increase or a decrease in the activity. There's equal probability of spoiling the activity and an equal probability of increasing the activity. So you begin to see how useful is this QASR equation. It gives me ideas about drug design, the sort of groups that I need to put in order to increase the activity, the sort of groups with the appropriate lipophilicity and with appropriate electronic properties in order to increase the activity. Here is another class of compounds, okay, basically phenanthrene compounds. Okay, phenanthrene compounds, okay, and the activity of these compounds, basically the antimalarial of these compounds is related to various attributes of the substituents at X and Y. So you have a little more complicated equation than I just talked about. Okay, so I have last five minutes to talk to you. Okay, I have to stop here. Okay, so let's see. Here is basically now an actual QASR table out here. Okay, so now here is 25 compounds have been synthesized. I'm not expressing which are these compounds. Their activities have been measured. Okay, here are these 25 activities. And from this onwards is your variables that are accounting for lipophilicity, electronic properties, and steric properties out here. So for example, polarizability has been calculated for these 25 molecules, and these are the values of the polarizability for the 25 molecules out here. The dipole moment has been calculated for these molecules. The potential area has been calculated. The hydrophilicity of the molecules have been calculated out here. And now what we are trying to do, we are trying to develop an equation for the biological activity with each one of these attributes. I want to know each one of these variables. Okay, the polarizability, how much does it contribute to the biological activity? The polar surface area, how much does it contribute to the biological activity? This is an electronic property. This is basically a property for the size and shape. And this is a property basically for the hydrophilicity. How much does the hydrophilicity of the molecule basically contribute to this? I want to basically get the QASR equation, some equation of this type. Okay, an equation of this type. In order to get this QASR equation, what we use, we basically use chemometric methods. Okay, to get an equation with, so what I will get, biological activity is equal to A times polarizability plus B times polar surface area plus C times hydrophilicity plus a constant D. To get an equation, to get these values of A, B, C, and D, okay, how much does polarizability contribute to the biological activity? How much does the polar surface area contribute to the biological activity? In order to get this QASR equation, we basically use what are called as chemometric methods. And there are a variety of chemometric methods that can be used, from very simple chemometric methods, okay, like MLR, okay, partial least squares, principal components analysis, stepwise regression, to some more sophisticated methods like neural networks. Today we talk a lot about artificial intelligence and machine learning methods out here. The neural network is actually the backbone of your artificial intelligence. We can use backpropagation neural networks. We can use CNNs, okay, convoluted neural networks, recurrent neural networks, which are better than CNN because they store information out here. We can use radial basis functions, random forest methods. We can use a lot of complicated chemometric methods in order to derive this relationship out here. Okay, since my time is up, I have to stop here, though I could talk a lot about QASR. Okay, so finally, what I'm trying to tell you is these equations between biological activity and the different attributes, okay, these variables, these equations is basically derived by using an appropriate chemometric method, some which I just listed out to you. You have to decide the choice of the chemometric method. After you have formulated this type of a table, okay, which is called as the study table. Okay, after I have designed the study table, to draw a relationship between this biological activity and this matrix of properties, I must choose an appropriate chemometric method to get your final QASR equation out here. And even when I get a QASR equation, there are a lot of other things. Okay, there is validation to be carried out. Primarily using regression methods, okay, or some chemometric methods. The question to be asked is basically, if I have such an equation, how do I know this is not a result of chance correlation? Okay, such an equation has not developed by a chance correlation. Okay, the chemometric method has not thrown up a chance relationship between my properties and my biological activity. How do I know that this is not a chance correlation that has been drawn up? So there is a lot of other statistics which we use in order to show you that our equation is robust, is sound, is reliable, is dependable. There is predictive value inside, and it's not a result of chance correlation. There's a lot of other statistical parameters that actually creep in. And some of the statistical parameters that actually creep in, we use basically the R square, okay, the regression coefficient. We use standard deviation in order to get an idea about this. We use the F values. Okay, we use confidence intervals. Then we use cross validations. Okay, we use cross-validation, we use bootstrapping. All of these techniques are actually used in order to show you that the equation that we finally develop by a chemometric method is not a result of a chance correlation, but it is robust, it is accurate, and it is reliable. Okay, so sorry that I couldn't talk a lot. The time is very short. Okay, so thank you all for your kind attention. I will have to leave at this point. I'm very sorry I cannot take any questions because I have a class. Okay, I have to teach my students at 12:30, so I have to run to the other class that is out there. So I'm very sorry that I cannot devote any time to question and answers, but thank you for your kind attention. And I hope I've been able to give you some idea.
Yes, sir, this has
thank
been
you so
very
much.
helpful. Yes, sir, we truly appreciate and we understand your prior commitments. Thank you so much for coming here. I hope that all the students who are listening and some of the questions can appear in the upcoming exams based on these slides that all the other speakers are also including. So I urge students to listen to these talks very carefully. Now with this, I move forward and would like to invite Professor Bhartam to deliver his talk. Before he does that, I would give a brief introduction. He is head of the Department of Medicinal Chemistry at our own Naipur Mohali campus, and he has done MSc in Organic Chemistry, PhD in Applied Theoretical Chemistry from University of Hyderabad. He has received many awards, most notably OPPI Scientist Award, Rambaxi Research Award, and he is a fellow of many societies like the RSC and ACS, and he is on the advisory board of many journals, and his major contributions are in the field of theoretical and synthetic organic chemistry, and he is involved in designing compounds and establishing the experimental proof of concepts generated using theoretical methods. He has been active in this area more than almost 30 years, and he has a lot of contributions. In those details, I would skip in the interest of time and hand over to Professor Bhartam so that he can enlighten us with his talk. Please, sir, over to you.
Okay. I'm very happy to note that there is this conference is happening, and this workshop is going to give lots of details to the participants regarding the drug discovery using computer-aided methods. I will be happy to speak on a particular topic. What is my way, how to share my desktop?
Sir, on the top, there should be some option.
Share. Okay, then I go to my PowerPoint. Can you see my PowerPoint?
Yes, sir. Please turn on the presentation mode.
Right.
Yes, sir, we can see this.
Right. I want to invite all of you to a particular process called 3D thinking. 3D thinking is not new at all, but we do not have the habit of thinking in 3 dimensions. We have to cultivate this habit. It is easy today. I am inviting you all to start thinking in 3 dimensions. Then I would like to invite you to learn how this 3D thinking helps in anti-cancer drug discovery. Okay, this is my title. My lecture is based on this particular message. The message given by Dr. Murko in the year 2018 in Journal of Medicinal Chemistry 2018. This particular reference, he has asked the question as a title of his article is, what makes a great medicinal chemist? A personal perspective. He was talking about his experiences, but one of the important message he is giving is that great medicinal chemist should have 5 to 10 important characteristics which are personalized for his. He should be having these personal properties. If he has these personal properties, the expertise in he has expertise in these 10 different varieties of topics. He will become a great medicinal chemist. This is how he wrote this article. I wish you all of you to read this article because this is giving a very good idea. Any budding medicinal chemist should cultivate 10 properties for himself, not about drugs. It's not drug-like properties we are listing here. It is an expert medicinal chemist. Okay, so out of this, one of the important messages that he gave is that the great medicinal chemist should be able to think in 3 dimensions. Whoever has become great in medicinal chemistry has got the ability to think in 3 dimensions. This is the message coming out of this article. I wish you to read this article. Having said that, what is 3D thinking? Why do we need to do? Why do we need to spend time on this particular topic? Are we not already thinking in 3 dimensions? No, we are not. Why? Our paper and pen, whenever we write a structure of a molecule on a paper, in 2 dimensions. When we write the name of the molecule, it is in 1 dimension. When we write when we look at the molecule in a round bottom flask, you cannot see what any molecule. You can only see a solid or some white solid or orange solid or some liquid. You will see only that. You cannot see the 3D structure, which is reality. Every drug molecule is realistic in its 3D structure, not in 2D, not in 1D, not in the round bottom flask. It is what it is in 3 dimensions. Drugs are 3D objects, macro objects. Your COX-2 or your GPCR or your cytochrome, everything is in 3 dimensions. The interactions between drug and macromolecules are also 3 dimensions. So then every drug and macromolecule and the interaction between these are all dynamical. They are dynamically changing. Sometimes there is hydrogen bond, sometimes there is no hydrogen bond, because the molecule inside the cavity of the macromolecule, it is undergoing a dynamical process. It is always undergoing some kind of change. It is like you are all sitting and listening to my lecture, but you are not sitting static. You are not statues. You are dynamical. Some of you are preparing yourself for lunch. You are already thinking, already 3 lectures are over. What is this 4th lecture coming? Can I spend time on this or not? Some of you are probably sitting in your bedroom and listening to the lecture. So there are varieties of dynamism you are already undergoing. Likewise, drugs are also not static. They are not statues. They are not rigid. They are dynamical. Macromolecules are also dynamical. When the dynamical small molecules, dynamical macromolecules are interacting, those interactions are in 3 dimensions. The strength of hydrogen bond, strength of a van der Waals contact or ionic interaction is going to be disturbed a little bit, sometimes increase, sometimes decrease due to the dynamical processes. This is all happening in 3 dimensions. The chemical in 3 dimensions. If a secondary messenger is generated, if a signal is generated from a receptor versus agonist interaction, if a secondary messenger is generated at IRTK, for example, producing a secondary messenger, it is being sent to GLUT4 to activate the GLUT4 and then by eventually taking the glucose into the cell. This is happening in 3 dimensions. Cells are 3-dimensional, organs are 3-dimensional, organisms are 3 dimensions. So if everything is 3-dimensional, why we are thinking in 2 dimensions? Why we are thinking in 1 dimension? It is not appropriate. So we need to think in 3 dimensions. This is a possibility today. Some time ago, this possibility was not there. In 1984, when I joined for my PhD, this facility was not there. Somewhere in 1993, this facility got started with the help of the molecular modeling. Before 1993, molecular modeling topic did not exist. After that, crystallography people as well as the computer-aided drug discovery people, they came together and they created many tools. There are several visualization tools available today. We can think in 3 dimensions using your computer, laptop, or even using your mobile. Okay, so it is not difficult at all today. So I am inviting all of you to only think in 3 dimensions. Forget about 2 dimensions, forget about 1 dimensions. That is a requirement if you want to succeed. Every successful medicinal chemist was thinking in 3 dimensions, he is thinking in 3 dimensions, will think in 3 dimensions. If you want to be in that category, people, you should cultivate the habit of thinking in 3 dimensions. Okay. It is today possible. You see that if you want to know what is Naipur Mohali, you can go to the drone view of Naipur. If you want to know about Naipur Guwahati, drone view of Naipur Guwahati will tell you that there is a valley in between several hills. Okay, so there is three directions of the Naipur Guwahati is hilly, and one direction is leading towards the some kind of a road. That road takes you towards the city. Okay, but you know very well that 3D is going to help you in that particular context. So drone view of Naipur Guwahati, probably they are going to show sometime soon during this workshop. Anyway, so the drug transportation is happening. For example, Metformin is getting transported through organic cation transporters. If it is transporting, how it is getting transported? What is the starting point of? Where is the end point of the channel? How it is swimming through a particular narrow passage that is created within organic cation transporters, which is actually a protein which is embedded in the cell wall somewhere. Or somewhere it is there. And so you should be able to think in 3 dimensions for that. Everything is happening in 3 dimensions. We should develop this habit of thinking in 3 dimensions. Pharmacoinformatics is a topic which helps you in thinking in 3 dimensions. With those things you are learning in this workshop. I will give you a simple example. Look at this example molecule. This is a wonder drug molecule. If you remember the structures, most of you may realize that this is nothing but isoniazide. Isoniazide was a wonder drug. Before isoniazide was invention and after isoniazide invention, there was tremendous change in the society. Because before this, all the TB patients were thrown out of the town. They were kept somewhere outside the town. Suppose that means all the citizens in your town, say for example Hyderabad, they all are thrown out of Hyderabad. They were thrown some small corner of outskirts, and they were all asked to live in tents, paying rent for the tent because they want to live, where all TB patients are living together. That was the situation before isoniazide was invented. The moment isoniazide was given to the patients, all the tents were closed. People started living in the city. So that means the TB patient is not thrown out of the city. This process stopped immediately after the invention of isoniazide. Now look at the 3D structure of isoniazide. What do you gain? You gain a lot more information. You have a flat ring, no doubt, but you have a pyramidal nitrogen also. The pyramidality was not clear from the isoniazide. So how do you think in 3 dimensions? you can use the visualizer. The visualizer software are freely available. Many freely available software are available. You just download them and okay, most of them are free. Some of them are costly, no doubt. You may pay or your institute may pay. This may be created for your PC. It is not very tough task. Okay. Now, what is the 3D? How the 3D is there? What is the background of theory? 3D, how it is actually defined? It is defined in terms of Z coordinates. This is called Z matrix. Z matrix means it is nothing but Cartesian coordinates. You remember your mathematics, X, Y, Z coordinates of your geometrical objects. You know how to find the distance between two atoms or 2 points in your mathematics. That is distance is equal to square root of x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square. X1, Y1, Z1, what is X2, Y2, Z2? They are nothing but Cartesian coordinates. So these are the Cartesian coordinates of the isonucleotide. You cannot remember, that is why visualizer is there. Visualizer is actually using the data provided in the form of the Cartesian coordinate matrix. Okay. Now, there is another way of doing it. This is called Z matrix coordinate. That is also known as internal coordinate matrix. Internal coordinate matrix contains only information regarding bond length, bond angle, and torsional angle. Once you have this information, you can define any drug molecule in 3 dimensions. This is how isonucleotide molecule can be defined using Z matrix. Cartesian coordinate matrix is different. Z matrix is different. Both are very much useful. One can be converted into the other very quickly with a software which works in 1 second. You can do that. This software was written long time ago. People are using even today. This small tidbits kind of software are available. Software package. There is software. There are software packages. We can use these in that. Now let us think of molecular modeling is a 3D activity. Any computer-aided drug design, molecular modeling, pharmacoinformatics, all of them are 3D in nature. So it is better to adopt this and forget thinking in 2 dimensions altogether. Because we have the facility today. Long time ago it was not there. Now you have. So it is important to think in 3 dimensions. Estimating the properties of the chemical species can be done easily using molecular modeling. Atomic level details of the chemical and biochemicals can be obtained easily using molecular modeling. Hydrogen bonding interactions, van der Waals contacts, ionic interactions, bonding patterns, polarizability, charge transfer, salt bridges. There are so many varieties of interactions inside our between drug and macromolecule. All of terms of molecular modeling, which is a 3D activity. Several misconceptions can be removed if you think in 3 dimensions. When you think in 1 dimensions, suppose somebody says a drug called Metformin is useful for anti-diabetic activity. Metformin, okay, maybe my Dadaji is also using Metformin tablets. Maybe Professor Vartam is using 1 tablet. Every day morning he takes 1 tablet of 1 gram of Metformin. It is a tablet, inside that there are molecules. There are drug molecules. Okay, very nice. That is information. But what is the internal details of this drug? Because I am not a user anymore. I am a scientist also. If I am a scientist, if I want to do medicinal chemistry using metformin, I should be able to think in 3 dimensions. I will give that example in the next slide. All the forces responsible for drug likeness. You might have heard something called Lipinski rule. There was a tool Dr. Sastry showed you today, Drulito. Drulito is drug likeness tool. It was created in Naipur Mohali. So that kind of things are good, no doubt. But there are forces acting inside. These are all can be estimated using molecular modeling. Molecular modeling offers many advantages, and this information is complementary to the information coming from experimental efforts. So there is so much information available: atomic level information, electronic level information, interaction level information, energy level information, dynamics level information. All of them can be easily visual estimated with the help of the molecular modeling techniques. So you might have seen several books on this topic. Let us take the example of metformin. First of all, let me tell you the structure of metformin. On the left hand side is the structure of the metformin. It is slightly small in the blue color. It is the structure of metformin. It has been corrected in the year 2005. The structure of the metformin was corrected. Till that time, all the medicinal chemists were silently writing it in the wrong. This is the right tautomeric state. Though it is right tautomeric state, now I am going to declare that metformin is not a drug. Metformin hydrochloride is a drug. Metformin is not a drug. Metformin hydrochloride is completely different from metformin. Let us consider the example. There is a boy who has given an interview for job. After giving the interview, he is waiting for the result. He thought that he has given good interview. He is confident, partly he is confident, but he is not aware of the competition. How much competition is there for him to get the job. So he will get the job or not, he was doubtful. He was waiting 1 week, 2 weeks, 3 weeks, no message was coming. He was hoping that he will get the job. He will be dull, he will be inactive, he will be somewhat depressed. Why the result is not declared? What is the delay? He is thinking in many directions. He is somewhat dull. But suppose he received the appointment letter. Immediately, what will happen to him? He will become dynamical. He will become jumping and dancing. He will buy the sweets. He will distribute the sweets across the city, across all his friends. Maybe he will do a big party, and he will prepare himself to go to the city to join for his job, and he will do many more things. Exactly like that. Metformin is dull, dumb, and useless. Metformin hydrochloride. Metformin captures the proton all the time, and immediately the moment it becomes metformin hydrochloride, protonated metformin. It is highly dynamical. There is no rigidity. It has lost many things. Look at that. It has lost conjugation. It loses intramolecular hydrogen bond. It lost resonance stability. It lost reduced. It has got reduced rigidity. It has gained a tool coordination bond. It gains extra electron density at the central nitrogen. It gains 2 lone pairs at the central nitrogen, whereas the central nitrogen carries formal positive charge. So metformin is completely something new. Look at that pink colored structure here. But the same thing, is it only theory or is it having practical applications? Yes, you look at the 3D structures, crystal structures of metformin. There are 2 forms of metformin polymorphs, 2 polymorphs, polymorph A and polymorph B. See that there is a conformational difference in 3 dimensions. Think about the structure. It is in 3 dimensions that I am already showing. structure of metformin. It has got two different conformers. The two are different in nature. One is thermodynamically stable form, the other is metastable form. Metastable form is more orally bioavailable. That means if I am preparing the drug before preparing the tablet, if I am having the bulk of my drug form B, it is going to be more efficacious than the thermodynamically stable form. You can see that 3D is providing lots more information about every drug. That is why thinking in 3D is very, very crucial. Look at this next one. Pharmacoinformatics is a topic which helps us in thinking in 3 dimensions. There are many other names, synonyms for this. As rational drug design, computer-aided drug design, molecular modeling for drug design, structure-based drug design, ligand-based drug design, in silico drug discovery, computational chemistry for drug discovery, computational biology for drug discovery, chemoinformatics and bioinformatics, everything for drug discovery can be called as synonyms. We are all intelligent people. Indians can easily adopt this particular topic. Why? Our mathematics is good. In high school, we learn good mathematics. Americans compared to Europeans, compared to everybody else in the world, Indians learn more logic. Our brain is logically trained and our brain is logically thinking. So we can easily adopt this pharmacoinformatics topic, and we can easily adopt the 3D thinking. So the technologies associated with this are already introduced to you. There is a technology, Dr. Narahari Sastry introduced a software which can do many things. Sir Coutinho introduced another topic, that is QASR. QASR, molecular docking, molecular dynamics, virtual screening, quantum medicinal chemistry, de novo design, chemoinformatics, bioinformatics, artificial intelligence in drug design. There are so many things today. This Dr. Narahari Sastry already mentioned. Professor Jem has also mentioned what is the conceptual things behind it. What are the cultures that a medicinal chemist has to adopt? Already we have touched upon today morning. I hope you are also already adopting these. But I am telling you, these are the technologies. These technologies are based on lots of science. Science is physics, chemistry, biology, no doubt. But within that physics, what is it? Within the computer science, what is it? Within the computer science, there is machine learning method. Within the computer science, there is the artificial neural networks. That means these are the science. The computer science is giving these opportunities. Physics is giving the opportunities called quantum physics, classical physics, then the Coulomb's forces, van der Waals forces, all of them are coming out of physics and chemistry. But you know very well, I don't have to tell you what biology is offering for drug discovery. Everything and anything in biology is required for drug discovery. Now I am going to go to more a specific example. I don't have much time left, but I will quickly go to this example. This is topoisomerases. These are the enzymes which are anti-cancerous in nature. These enzymes are undergoing isomerization. That's why they are called topoisomerases, where the topology of the enzyme is changing. That means this DNA is known to all of us. DNA is stored inside our brain in inactive form quite often. Topoisomerases convert in DNA into active form and thus increase the cell replication. That means cancer cells which are undergoing the rapid replication and rapid growth, because of the because of the topoisomerases, which are causing the topological changes in the DNA. That is the idea behind this particular set of examples. We have to understand what is going on. It may be breaking one strand or two strands of the DNA, and it can exist two types. The topoisomerase 1, 2, 2 alpha, 2 beta. There are varieties of them. And the human topoisomerase 2 is what 2 alpha is what we want. Now come back to the 3D thinking. Look at the two structures here. The two structures here are same molecule. I am showing in two directions. One direction is you see the pink colored lines in between the 3D structure. That is nothing but DNA. Then the rest of the molecule, green colored and the blue colored, is nothing but the dimer of the topoisomerase. So here I am showing it in two directions to show the cavities available. Binding domain is one cavity, ICRO binding domain is another, etoposide binding domain is another, etoposide interactions are another. There is C-terminal domain, there is N-terminal domain, then there is a catalytic domain. There are many other things available in the 3D structure. We have to think in 3D. These are all the crystal structures available which will help us in thinking in 3D for the topoisomerases. Now, then what happens? This is a knot. The knot has to be relaxed. The strands of the DNA pass through the enzyme, and look at that red colored strand and the blue colored strand. Both are going through the enzyme. Enzymatic dimer I am showing here. G segment passes through first, and then the T segment goes. The G segment gets broken into two parts by the enzyme, and then T segment passes through that. As a result, the tension in DNA is relaxed. So this is a catalytic cycle. Look at the 3D structures. There are several. You look at A, B, C, D, E, F in this graph. A is a 3D structure, B is 3D structure. Look at the difference. The C terminals are connected to each other. Blue colored and green color, very small structures, may not be very clearly visible, but I hope you are able to follow. But the central domain is distancing about 25 to 30 angstrom. But once the G segment enters, the distance gets reduced. And once the distance gets reduced, then the DNA gets broken. And then once the DNA is broken, T segment enters, and the T segment pushes the entire process, and then the DNA breaking, and the one PO bond is broken, another PO bond is formed. And the next step number 5, the T segment passes through, and then in between 5 and between F and G, the G segment resealing of the DNA happens. DNA is broken, DNA is resealing. These are the two activities. So as a result, if you are able to, I think you are not able to see me, but you can see there is a beautiful dynamism in this particular enzyme. All this is depicted in this figure. These are the compounds which can inhibit the first step. Second step, another set of compounds to inhibit. Third step, another set of compounds. Fourth step, another set of compounds. Another set of compounds. There can be many inhibitors. Based on that, one can design many new molecules. These are all to do drug discovery: sequence alignment, homology modeling, molecular docking, molecular dynamics, binding energy estimation, quantum chemical analysis, and pi mole analysis, as well as to visually inspect the dynamism. All these things are possible using computer-aided methods. Now, that is what exactly was done in Hypermohali. I'm giving an example of a work done by Professor Guchait from Organic Synthesis Lab, and from our lab, Computer-Aided Drug Design, and Professor UC Banerjee Lab in Biology. And there is another collaborator from Bhubaneswar. 4 groups of scientists and their students. Together, about 20 scientists have worked on this topic for the past 10 years. So the story I am telling quickly, in 5 minutes, I'm going to declare the entire story. What happened was initially a particular compound, series of compounds were designed to bind at the ATP binding domain. I already showed you that ATP binding domain. Inside that, these class of compounds are binding. These are known as N-fused imidazoles. These compounds are binding at the. That is very good. How do you prove that? You can do molecular docking. You can do biology. Inhibition is happening. And then they are competitive to ATP. That means they are not allowing ATP to bind in the same cavity. This was the story. Very nice story. It was published. It was accepted. Very good. Tali baj gaya, ho gaya. And that particular work is being referred many times. Very good. But based on this work, the organic chemistry team has designed slightly larger molecules. Then molecular docking team was asked to help. Molecular docking team said that, okay, first series of compounds are docking very well, but the second series of compounds well. That means the second series of compounds will not show ATP competitive inhibition. That is declared by molecular docking team. So that means immediately it is a message to organic synthesis people, do not waste your time. Don't use your chemicals and biochemicals. But by the time the docking exercise was completed, the synthesis work was also completed. So because the chemicals were readily available, students were working hard, and so whatever synthesis was done, and so chemicals were readily available. Since the chemicals were readily available, they were already submitted to biology. And biological team said that inhibition of topoisomerase is happening. So what is the message? Molecular docking and computer drug design team is telling, do not even waste your time. This will not show inhibition. And the biology team is telling topoisomerase inhibition is happening. That means messages. Both are contradicting with each other. Then it is perplexed, the situation. So the team, there was one option for the entire work. One option, that option is forget about entire research and do some other work. This is not going to help. This is one way of doing research. Another way of doing research is do not leave anything. Continue. Find out why is it like this? Why molecular modeling team is telling something different. If they are giving contradictory result, should I run away from the project or should I continue and try to resolve this contradiction? This is the choice that was made by the team. These are all the various new compounds that were synthesized and molecular docking was done. And molecular docking, you see that pink colored inside on the right hand side, ATP binding domain, and then yellow colored molecules are the new series, and the pink colored molecule is buried inside, that is the old series. First series of compounds were successful, second series were not successful. This is docking result. So what is the meaning? That means cytochrome inhibition, no, topoisomerase inhibition can happen with the pink class of compounds, and it does not happen with the yellow colored class of compounds. Okay, so if that is true, docking always gives something. Let us don't give importance to docking. This is another message that could have been given, but the team did not want to do that. They want to see why docking is giving this result, why biology is giving that result. Then they went to the biology team one more time. They have given a challenge to biology team. They have given another challenge to computer team. That means both of them teams have decided not to give up and continue the work. Why is this like this? Then they have done further analysis. It was found experimentally that ATP site is not being inhibited by the next series of compounds. That means first series of compounds are inhibiting the ATP binding site, but the second series is not inhibiting according to biology also. That means computer-aided modeling as well as this extra biological experiment giving you the same result. That means it is contradiction is removed. Complementarity is happening now because ATP binding inhibition cannot happen according to the biology, but inhibition of the topoisomerase does happen. That means what is the challenge to the molecular docking team? So can this molecule, if not the ATP binding domain, where is the binding site for the newly designed molecules? This was the question given to the molecular docking team. So we have to find the entire cycle one more time, understand so many sites, such a big, huge molecule, macromolecule, where are all the sites where the can happen? That was the question. Then binding site is not N-terminal domain. Then it may be similar to Merberon binding domain. One clue was obtained from literature. Then another clue, Merberon binding site was not known to us. So find out the Merberon binding domain site. It is close to the etoposide binding domain. Then what to do? Where is the binding site of Merberon? Question and answer this question. Merberon binding domain is very close to the DNA binding domain. That means probably Merberon binds in the vicinity of the etoposide binding site with an overlapping interaction domain. So you do the molecular modeling again, you understand the metal magnesium interactions, then you go to the docking again, then you design the surface versus the drug interactions, DNA versus the drug interaction, calculate the docking score, calculate the dynamical score, do a lot more research that the investigated compounds, some of them are inhibiting the Merberon binding domain. And thus, you know very well what to do, and you have the linear equations. You can find out the you can inhibit using biology, and then you can get the micromolar activity, macro molar level information, and then you can realize that there is a switch. The switch that happened is that the new series of compounds are binding at the Merberon binding domain. They are not binding at the novobiosine binding domain. That means they are not competitive to ATP. They are competitive to Merberon. That means a switch is happening in the site of the action for the series of compounds. That is how new series of compounds are also inhibitors of old series of compounds are also inhibitors of topoisomerase. Then you dock the old series at the Merberon binding domain. That then it will become clear old series of compounds bind at the ATP binding domain as well as at the Merberon binding domain. So likewise, the results were given, and there are many other results. Surface properties were understood, quantum chemistry was understood, then the docking results were understood, then interactions were understood, and finally it was concluded that the as well as two second series are sufficiently inhibiting and sufficiently showing anti-cancer effect. How is it possible? It is because thinking in 3 dimensions was done. So now I will stop my lecture. I think I already crossed by 5 minutes or so. So thinking in 3 dimensions helped in bridging the gap between biological team and organic chemistry team, as well as the drug discovery. Thinking in 3D is an essential component of drug discovery, which all of you should adopt. This is my message. Thank you very much.
Thank you very much, sir, for helping us understand how to think in 3D and how it can be applied to real life medicinal chemistry problems and how teamwork can come to solve such complicated problems, and modeling can give us insights into these complicated issues. So we can take one or two questions if there are any on these teams, people who are online or on the chat box.
Sir, we request you to please stop sharing.
Okay. How to do that? Stop sharing. Okay, where is it? I don't know. Stop sharing. Yes. I think I am not visible.
You have to turn on your camera, sir.
Right.
Yes, sir.
It is
Thank
very cold here. You can see me, my
Yes, sir.
very, very cold in Mali.
Yes, sir. Here also getting somewhat colder in the last 4 or 5 days. So thank you very much for nice. It was nice and pleasure for us to have you and
Okay,
listen
very
from
nice.
you
Best
time.
wishes for the entire conference. And I'm very happy to see my teacher as well as my students giving in this lectures in this conference. Fine.
Yes, sir. Many times I felt I'm back in the M-Form days of Naipur Mohali in the I'm sitting in the class. So with this, we again thank you very much, sir. And with this, we would like to pause for here for the lunch break, and we will resume again at 3:30 for the OpenAI software session. And there will be also talk by Professor Kharkar. So please do join us back then again. Thank you very much.
I'm all set.
So can you already share your screen so that I will have some context while introducing you?
Sure, no problem. I'll just.
Okay, sir. Yeah. So good afternoon, and once again, welcome to all of you. So I'm happy to tell you that we have with us Professor Prashant Kharkar from ICT Mumbai. He is a professor in the Department of Pharmaceutical Sciences and Technology. He did his master's and PhD in pharmaceutical chemistry from ICT and did postdoc at Wayne State University, USA. And he has served many institutions, including NMIMS, where I had the good fortune to be his colleague. And then, but his greater achievements has taken him places, and he is now working at ICT. And he is expertise in design and synthesis of and biological evaluation and preclinical development of many chemical entities. And he works also in material science in potential for the discovery of potential anti-tubercular agents and many more for the computational prediction of toxicity. And he is also consultant for the OpenEye software. And today he is going to show us MOE related demos. But before that, he is also delivering a talk for the benefit of the students and other researchers on the topic of computer-aided molecular design perspective. With this brief introduction, over to you, sir.
Yeah, thank you so much, Dr. Vaibhav. It's indeed a pleasure to be here and talking to all young and bright minds. Let me just try and share it one more time. I think I have used this PowerPoint live. Let me just share my screen. I'll be back just in 1 minute. Huh?
No worries, sir.
Yeah. Yeah, now it's perfect. Is it seen now? Is it visible?
Yes, sir, we can see. Please go ahead.
Yeah. Great. Thank you so much, Dr. Vaibhav. Like I said, I'm very, very happy and excited. And then, of course, the session is for demonstration, and I'm going to share some of my experiences in terms of my own struggles and while getting into this field, right from my master's day back in 1998. And I have been very obsessive about the way this whole thing happens in terms of even the use of term like computer-aided drug design, which was earlier a very famous term, but then after spending so much time in the drug discovery companies, we have realized that I mean we all know, we all read from the literature or from the papers that discovering a drug is a very, very difficult thing. It takes like so much money, so much time, and you don't know whether it is really whether the candidate will really become a drug or not. And then we have like I have my own success so far in terms of we have two molecules entered in preclinical, two molecules which entered in preclinical phase 1 clinical trials after successful preclinical studies. So one is for triple negative breast cancer, and it's a cancer stemness inhibitor or cancer stem cell inhibitor. So this is a new thought process in anti-cancer therapy, where the cancer stem cells are the ones responsible for so-called relapse of cancer. and that's where we want to actually cut the roots of cancer by killing these cancer stem cells. So we have got the IND approved, or investigational new drug application approved, and then the phase 1 studies in triple negative breast cancer patients will start in April first week. Apart from that, we also have one new chemical entity, which is a viral entry inhibitor, and it has shown excellent efficacy in animal models of SARS-CoV-2 or COVID-19. And then that IND also we have got the approval, and the phase 1 studies will begin somewhere in May. And at the same time, we are also filing the US INDs for both of these molecules. So this is along with or in collaboration with a company called Godavari Biorefineries Limited, where I work as a consultant, and it's almost 9 years of our association that we work so hard to get this molecule to get these molecules this far. And so that's where I'm going to talk about. So the point of the reason behind mentioning these facts or these things is just to tell you that we have worked so hard to get to this stage. So then when I say drug discovery is difficult, I mean it. I have experienced it. Not just I'm not just talking in the air or from the literature source, right? So coming to my first obsession of calling computer-aided molecular design. I mean, earlier people used to call it as CAD, but then purposely I have removed this drug word, because when you use computers for discovering a new chemical entity or designing a new chemical entity, which may be a better version of what you would want it to be, then in that case, and it's a molecule, whether it will become a drug that will only be known after successful clinical trials. So computer-aided molecular design, an overview or a perspective, this is what I'm going to briefly talk about. I will rush through slides so that we can spend more time on the demo part. And I'm sure most of you are beginners in this field, so I assume that, and even if you are kind of more mature or an expert in this field, but I can always share my own experiences, and this field is so vast that we learn every now and then. I mean, I don't say that I'm an expert and I know everything, absolutely not. So I'm still a learner. I learn every day a new thing whenever I work on projects like this. So we are all on this. We are all on the same level. So first of all, thanks to the scientific community organizers of this particular conference or webinar, and of course you all participants who are willing to learn something new and willing to spend your time for that. So again, I usually put this slide before all my talks, where whatever views, ideas, and opinions, they are solely mine. You may not agree with them. They may be in contrast with what is already known in the literature or what is already regarded as right, or I beg to differ, and that's how we researchers are. We all are researchers, so we agree to disagree. And with this, I would just start with my talk. So computer aided. So again, I'll tell you one incident. When I joined immediately after my PhD, I joined Piramal Life Sciences, which was Nicholas Piramal India back then. And then they were all excited. So we started working on this anti-diabetic project. I did some molecular modeling studies for them, and they were so excited. So they made the first molecule, and then instead of taking it to the in vitro studies, they directly took it to the animals. I was telling them it's not, it's not probably going to work. We don't know anything about its cell permeability or cell, permeability and other things. And they were like, no, it looks so interesting, so impressive, nice pictures and stuff like that, and it completely failed. It did not show any animal efficacy. So the point again behind sharing this particular incidence is it is computer aided. Right? It's not computer molecular design. Computer is not going to design a drug for you. You are going to provide your ideas to the computer, and computer will aid in refining those ideas. So as the very first lesson is, it is just a tool. It is not some magic box. You have to understand its limitations. I mean, you are trying to study something which is happening in so complex environment under biological conditions, and you are trying to study on a computer screen where you can see receptor, where you can see the ligand, and you are trying to put them together, and then we are actually ignoring a lot of things, including the solvation, desolvation process. So whatever we are trying to study, say molecular docking, it is an oversimplification of what happens actually at the biological level, and that's where the differences between the predictions and the actual experimental results happen. Meaning, I challenge anyone who is present here or in the scientific community, if you are doing some molecular design, you have some docking score, and then you have some experimental results, there will be hardly few instances where you get a nice correlation where you say it's a significant one, and most of the times it just falls apart unless you account for the other phenomena, including the solvation, desolvation. Of course, there are advanced computational techniques to do that, and this is where one has to understand the limitations, capabilities, and the overall outcome when it comes to. As a student, we are all very excited. Oh, there are some nice pictures. I have a receptor. I designed molecule. I threw it to the receptor, and receptor. I mean, the algorithm gave me some very interesting outcome. The molecule is binding perfectly, but when I test it in the assay, I don't see any activity. So the expectation between reality and the hypothesis or prediction, this is where the first mistake we do, and I have learned the hard way from my own experience. So one has to take these things very with a pinch of salt, right? So the thing is, who designs molecule? It's us. The human brain designs molecule. And again, I'm going to share some tips or some tricks with you in terms of if you really want to be a good molecular modeler or good drug designer, you really need to be a good chemist. In the sense, your understanding of chemistry will dictate your success as a molecular modeler or as a drug design expert, right? And this is where understanding the chemistry is central to understanding drug design, understanding molecular modeling, and this is where I would advise to be very nicely familiar with the chemistry, including the functional groups, the structure, the conformation, and then the molecular properties and how do they arise, how they actually have something to do with the drug action. So understanding that is very, very important. I will skip this part because this is a drug discovery seminar, so I'm sure you'll be hearing this from many speakers. So I will just skip this part. You are aware of molecular docking, or somebody some expert will definitely talk about molecular modeling and stuff like that. So I'll just skip this part. Again, you all know the current numbers are $4 billion to bring a new medicine to the market, and only 5% of the drugs which essentially get into the market or get into the clinic are able to bring the return on investment. Otherwise, most of them, they actually are loss-making endeavors. Out of these 4 billion, 60% goes on development, where you do not, as a molecular modeler, as a chemist, as a biologist, where you do not absolutely have a control how the molecule will turn out in the clinical trial. And this is where one has to really understand the gap between the drug discovery and development, meaning the success rate, the attrition which happens mostly in the clinical trials, phase 2 or phase 3 clinical trials. And this is where one has to really be aware of what can potentially go wrong, and you be ready with that, right? Meaning, say 10 molecules get into the phase 1 trials, only one molecule becomes the drug, right? So 60% of the expenses on development, and then 20% each on discovery and preclinical stages. Return of investment is awfully low, but still the global pharmaceutical industry makes $300 billion in profits every year. And most of the expenses in the drug discovery and development goes on the advertising. Believe me, this is a fact. And I mean, at times you don't really, you may not agree, but this is is the fact actually. So coming back to molecular design, so again, this is an approach to tailor-made new chemical entities. Now, in the poster session, we have heard, at least I have attended 2 of them. So one student has designed, along with her mentor, designed some interesting molecules, and then she's synthesizing that, and then. Right. So when it comes to design part, like I said, you have to be a good chemist. That's first thing. And then understanding how the ligand or how the molecule is interacting with the its molecular target or macromolecular target. That is another very interesting thing one must actually be aware of. Right. So it is an approach to tailor-made new chemical entities. And when it comes to design, again, understanding the toxicophores or the groups which are likely to introduce toxicity or the groups which are likely to be more problematic at a later point of time, one has to really build in that right away when you are designing the molecules. So there are strict no-nos when you are trying to design the drugs. Say a nitro group, you don't really want a cyano group, you don't really want a sulfonic acid, you don't really usually want a sulfonamide, although there are many drugs containing sulfonamide. You don't want a drug containing furan ring, you don't want a drug containing thiazole ring, you don't want a drug containing thiophene ring, because they are likely to cause problems at a later point of time. You also don't want a drug which is capable of getting converted into quinone, just the way paracetamol would get converted into. And that's why, there are so many stories from which we can learn. There are books devoted to organic chemistry or medicinal chemistry of functional groups, where it has been very nicely summarized as to how does each functional group contribute to drug receptor interaction, and how does the same functional group also contributes to the overall pharmacokinetics and drug action, including pharmacodynamics. And as a student, you can always read voraciously and learn. Don't be too harsh on yourself that you get it right in the first instance. As in, even I don't say that after spending so many years in this field, I don't say that I am actually a good drug designer or something. I know fairly well in terms of what things will work, what things will not. This is what you have to be humble, no matter how good you are at these stuff. But then, like I said, your knowledge is going to make you or break you, and getting knowledge is one best way is to read scientific literature, right? So really, if you really want to be a good molecular modeler, again, apart from being a nice chemistry expert or a person who knows chemistry well, you also need to understand what people are doing, what is happening in the scientific world, in the literature, and how you can borrow those findings from the literature for your own research. And this is where the creativity aspect of you can always explore. But that creativity will not be possible unless you read, right? So typically the main emphasis in drug design is always on potency, meaning more potent the drug is, lower dose would be, and then lower side effects would be. So potency will always be there. Then selectivity, if there are similar receptors present. So say in case of kinases, there are 500 different kinases present in the body. So if you're targeting one particular kinase, you are also likely to target the housekeeping kinase, which will get into the toxicity mode. And this is where selectivity comes into picture. And then pharmacokinetic profile, again, this is you're walking on a tightrope, and there is a valley deep down, and you are just walking on that rope. You don't want to fall in the valley. At the same time, you want to go to your destination while walking on that rope. And this is where drug design is very, very tricky. It's not impossible, or it's not difficult. It is difficult, but then you really have to do it smartly to given the amount of resources we have at times. Then another issue is, of course, toxicity issues. Like I said, those toxicophores you must avoid. So then who is the one designing these drugs? It's human mind. It's you and me who are designing that. Computer is just a tool. Computer is just helping you to test your hypothesis. You may have 100 hypotheses. Computer will do test those hypotheses and prioritize those hypotheses so that you can go with the top ranking hypothesis. And there is a probability of success, very high probability of success. And that's where to optimize the drug properties quickly, rationally, intelligently, inform, and you have to use, as in the molecular design, computer assisted molecular design is going to help you. So because during this whole cycle or in this whole process, you have to decide at different stages, go, no go. Meaning if you decide no go where it is actually go, I mean, you would have taken that risk, then you would have succeeded. If you decided not to go ahead, and that's where the program got stuck, or probably it would involve more expenditure, more time just to reach to where you would want to. Right, so this is where computer-aided molecular design comes to picture. So the hypotheses are generated by bright minds, are tested by the computer. And of course, the best part with computer-aided molecular design by now, those who are already working in this, they have realized you can generate any molecule. As in, if you give the Lipinski's rule of 5 filter limits, and then given the amount of, or given the elements present, carbon, hydrogen, nitrogen, sulfur, oxygen, phosphorus, silicon in some, and then halogens. So you probably will come up with 10⁻⁶ molecules. And how many molecules we have made? Well, really a tiny fraction. As in, if you see what is the time since Big Bang has happened, it's approximately 10⁻⁷ to 10⁻⁸ seconds. So even if we started right when the Big Bang happened, we would have still made only 10⁻⁷ molecules. So again, what I'm trying to tell you is the possibilities are enormous. But then you can generate any molecule, you can design any molecule as long as you have passion for it. Believe me, you will come with very, very interesting designs, interesting molecules. But then chemistry, feasibility, the synthetic chemistry may not be possible with some of them. And not every design which you make will be able to bind to the receptor. Not every design will have all the potential I would say potential, like good pharmacokinetic properties, less of toxicity issues. But then that's where you have to, it's like finding a needle in the haystack. But then that's where computers can actually help you. So you all are aware of structure-based drug design when you are using the three-dimensional structure of the macromolecular target and finding the binding of your designed molecule with the macromolecular target. So that is structure-based drug design. In the absence of the three-dimensional structure of the molecule, it is ligand-based drug design. Ligand-based design. I will not spend time doing that. So when it comes to structure-based design, like I told you, whenever you are doing, say, molecular docking, then in that case, it is oversimplification of what is happening. But then molecular docking is extremely useful tool in terms of quickly testing. What if I change a group to this? What if I change the conformation? What if I put a substituent instead of para to the meta or to the ortho position? What will happen to the conformation? So you can quickly test, and most of the times it will be fine when it comes to finding the binding site complementarity and how this molecule will be interacting with the site. But then the problem is, like I said, when it comes to solvation, desolvation, that at times it becomes very difficult. Although there are high-end algorithms which can tell you those strategically located water molecules. In fact, I think 2 or 3 days ago I read there is one very interesting article in Journal of Medicinal Chemistry where they actually tried to mimic the strategic located water molecule, and they could increase the potency tremendously, and that was a huge success story. So likewise, I'm saying when you want to actually simulate what happens in the in the biological context, or at the macromolecular level, or at the molecular level, you can't really ignore water molecules. Those water molecules are extremely useful, and in fact, when you prepare the protein structure, most of the times you will probably delete water molecules away from the active site. But then, at times it is difficult to really retain all the water molecules and find out. But again, like I said, you have to try out different things and come to a good conclusion, which will, where there is good agreement between your prediction and the experimental result. So then comes ligand-based drug design. Pharmacophore design is, where, and I'm personal fan of ligand-based drug design, although I've done a lot of molecular dockings, but ligand-based drug design design is, or ligand-based design, molecular design is where I'm more comfortable. All you need is a good set of structurally diverse and active molecules, and of course, if you have inactive molecule, that will also add to the generation of a very robust pharmacophore hypothesis. And you start with that, and because it's ligand-based, so computational power requirement at times can be minimal compared to, or less compared to, what otherwise you would do in if you have a macromolecular drug structure. So in that case, macromolecular target. So in this case, all you have to do is generate the pharmacophore, and you have a database of small molecules, and just find out which of those molecules align with the pharmacophore. And those pharmacophore searches usually are very quick, and eventually you get the hits. In fact, OpenEye scientific software has got a great capability in terms of, so they've got two different modules. One is ROCks, rapid overlay of chemical structures, where the shape complementarity along with pharmacophore complementarity can be quickly assessed. And they do also have another module called EON. So EON basically takes care of electrostatic complementarity. Now again, why steric and electrostatic complementarity when it comes to say you're talking about ligand-based drug design? So you already have a molecule which is a known inhibitor or a known modulator of a macromolecular target. Now you have to find drugs, or rather you have to find molecules which are essentially similar to this this particular potent molecule or potent inhibitor, but then you want your molecule to be structurally diverse or different, so that you can file, or you can file the intellectual property like patent for that, meaning you are trying to generate novel chemical matter. So in that particular case, finding out what molecule will match not just the pharmacophoric feature in terms of the structural complementarity pharmacophoric features, but you also would want the electrostatic complementarity. In this sense, you don't want a negatively charged group in your molecule to be colliding with a negatively charged residue in the macromolecular binding pocket, right? Because that's a strict no-no, meaning there will be repulsion and your molecule will never be able to bind. Now, just imagine if you were to, you are blindfolded and you are asked to move around in your campus. So what are you going to do? How are you going to do the sensing? Probably, as in, we are not as good as dogs to sniff and then find out the smell, but we are good at touch, meaning you are blindfolded and you are just moving around and sensing what is around with your hands, right? So this is exactly what happens when a ligand approaches the macromolecular target. Molecule doesn't have eyes. The macromolecular target doesn't have eyes, and you're talking about body. Suppose your macromolecular target is located in the brain, say dopamine receptor, it's present in the brain. So your molecule has to go right from, if it is orally administered drug, right from the site of administration to the site of action. So you can, I will not go into the details of those. So it has to cross many hurdles, and by the time it reaches everywhere. It will also reach to the site of action. And this is where, when they are approaching each other, the first sensing that happens is electrostatic interaction forces, because these are long range interaction forces, meaning a negatively charged group in your molecules ligand and a positively charged residue. So those are long range interactions. So they will sense each other and eventually they'll come together and bind. So the first thing happens is electrostatic sensing, and then you have the next part is structural complementarity, meaning the lock and key type mechanism. Only one lock can open, or only one lock can be opened by one key, right? So this is what happens, and this is exactly why you would want to have shape complementarity as well as electrostatic complementarity, and OpenEye has extremely powerful tools to do that. In fact, I have published 2 or 3 papers basically with the theme of computational repurposing. I can share those papers with you. So basically what we did was we took a lead molecule and we used these 2 modules, ROCks and EON, to come up with a very interesting set of molecules, that is drugs for repurposing. One we did in 2016, we published in RSC Advances, and that was for Ebola, when there was Ebola outbreak in the Europe. And then fortunately, at the same time, somebody evaluated a library of drugs experimentally against Ebola, and we were so happy to see that there was much of overlap between our computational results and their experimental results, and this is how this paper appeared after we communicated to the journal. It was reviewed, and they were saying the experimental proof has to be there. And fortunately, we found this paper which appeared around the same time, and we could convince the editors, and we got it published. So the point is, OpenEye has got extremely cool capabilities in doing the ligand-based drug design. Right, so we will discuss that at a later point of time. And then you also have other tools, the cheminformatics tools, which include QASR and then 3D QASR, 2D QASR, and then a lot of other stuff, including machine learning and deep learning. But I will skip this part, right? Then bioinformatics, again, it's altogether a different ball game. I'm not a bioinformatician. I know things, but I wouldn't call myself as a bioinformatics guy. I am a cheminformatics person, right? So when it comes to bioinformatics, it deals with the biological information, which include the gene expression data, and it involves understanding the genetic basis of a disease and how the genomic or genomic changes affect the disease state, and how the molecule can be essentially useful in a particular state in other case. So basically, bioinformatics is more, I would say, more useful for precision medicine, where one drug for one person, meaning that that's exactly what happens in oncology. Many drugs, many of the oncology candidates, they do not really work for every patient, and that's where they will screen out certain biomarkers, screen for certain biomarkers, and if that biomarker is present, then only that drug will be given, so that there will be a higher chance of success, in the sense the therapeutic outcome. But I will just not worry about this. There also machine learning and deep learning approaches are used. Coming to CAMD history, I'll skip this part as well. It's been since 1960s that we are into the ligand-based approaches. 1964. The Hansch QASR approach was proposed, LFER, linear free energy relationship, and then there came Fujita-Ban method, and then a lot of other things came. In 1978, the molecular shape analysis was proposed. That was one of the earlier methods of three-dimensional QASR, which extremely did well. And we had this active analog approach, where you try and find out why certain set of molecules are inactive, why certain set of molecules are active, by aligning with a molecule. Say I have got an active molecule, I have got an inactive molecule. If they're structurally similar, or even if they are not, I will try and align them and try and find out which part of inactive molecule does not align well, or if there is any additional part which might be kind of sterically clashing with the receptor, and eventually bringing down the activity or making it completely inactive. Right, so most of those, and then came with the advances in computer hardware, software, and computational power. In 1988, 3D QASR technique like COMFA, comparative molecular field analysis, was introduced by Sir Richard Kramer, and then there were many similar techniques which were introduced. Right, and then in 2003, Human Genome Project was completed, which actually made a lot of macromolecular targets available for exploitation for drug design, and many success stories arose out of that. So I would say, by today's standards, the technology has matured comparatively what we had like 2 decades ago in terms of the tools available. And nowadays, the machine learning tools, as well as artificial intelligence tool, or even for that matter, deep learning tools, they are from the same genus. So they are all making news. And in fact, there was a company who claimed to have found out the target by artificial intelligence, molecule by artificial intelligence. There was an interesting article in CNN, and then so much. But I, as a drug designer or as a medicinal chemist, I have my own reservations about their claims, because not a lot of things. I mean, not everything they have revealed, and we don't know what is there, what they are not saying about it. And then when it comes to computer-aided molecular design, nobody is stopping you to use a combination of a structure-based approach and the ligand-based approach, provided you have the three-dimensional structure of the macromolecule available. And then nowadays we also have three-dimensional structures available from cryo-electron microscopy. 3 scientists were awarded Nobel Prize for in chemistry in 2015 for their discovery in cryo-electron microscopy. So that is making a wave. In fact, in 2017, I attended one GRC, that is Gordon Research Conference on Computer-Aided Molecular Design. So it was like 5 days full pack program. The last session was by Dr. Sriram from Stanford University. 45 minutes that guy talked and he stole the thunder. All 5 days, all the speakers were on one side and this 45 minutes were on the other side. And he spoke on cryo-electron microscopy and his own research on that. And that was amazing, right? So what I'm trying to tell you is there are advanced tools, experimental tools are coming up, advanced computational tools are coming up. So drug design or other molecular design is no longer be similar to what we used to do when I was a student. So again, you guys are lucky to have all these tools available to you. And this is what I'm going to share, because we have seen those gaps. Or we have seen those days where we had to really struggle with the computational power. Nowadays, we have access to supercomputers. You can buy supercomputer time from CDAC or others. And Dr. Vaibhav has already done that high-end computations. So he's an expert in that, right? So there are so many advances which has happened. Success stories, several success stories. HIV-1 protease inhibitor, Imatinib, was claimed to be the first rationally designed drug which came out in like 5 years, and then it became a blockbuster drug. And then the resistance developed. Then they developed a second generation, third generation BCR-ABL inhibitors. Again, it's a tyrosine kinase inhibitor, and there are many. And now, if you look at kinase inhibitors itself, there are more than 60 kinase inhibitors introduced so far, and many of them, those are blockbuster drugs for cancers. So these are all molecularly targeted therapeutics, and most of them, they have come from computer-aided molecular design, and that's an amazing part of it. Right. In addition to that, you can also predict the physicochemical and toxicity properties using the artificial intelligence tools, or even I would say machine learning tools. There are many free tools available on the internet. So my sincere advice to all the students who are beginners in this field, whenever you design a drug, the first thing you should be doing is pass it through some of the widely used tools, freely available tools like there is Swiss Admin, and there are plenty of other tools. Just pass it through that and see if there is any problem. For toxicity, there is a tool called Protox2. Just throw it through your molecule. All they need is structure, and they'll predict. And the predictions are fairly accurate. And like I said, the toxicophores, you should look out for toxicophores. You should look out for toxicophores in the sense that those toxicophores should not be part of your drug design. There are plenty of examples, plenty of literature available. I'll not get into that. So, if you can get into machine learning and deep learning, believe me, you will not repent of spending or investing time. So there are a lot of tools available, free tools available on GitHub. All you need to know is download, and you should know how to use them. And those are amazing tools, and you can actually use. There is a NIME. There is a tool called NIME, which was actually the funding of the development of that was funded by my previous company, Nycomed Pharma. It's KNIME. NIME is Constance Information Miner. It's amazing tools. Many of the Schrodinger tools are available on NIME workflows. So and it's freely available. So if you learn NIME, in fact, there were few faculties in NIPER Mohali. I think Abhay Sangamwar or something. He was an active user. I don't know. I haven't really followed him after since last 2-3 years, but I have read his papers. Amazing work. Most of the work based on NIME. So what I'm trying to tell you is it is possible. It's just you have to look for those tools. You need not say that I need all those high-end or expensive softwares. There are a lot of free tools available. And then there are success stories from my lab. This was the work which after I left Nycomed. So basically, we could carry out a moderate or medium throughput screening experimental screening where we actually screened 50,000 compounds in GVK in Hyderabad. I mean, of course, my company was involved, not that entirely we did ourselves. The compounds were sourced from the company, and we could actually do it. And we so again, the target is human IMPDH2. It's for cancer. It's again for rheumatoid arthritis or ulcerative colitis, many things. So this is an interesting paper. We could actually get at least 4 or 5 moderately potent molecules and structurally diverse molecules. So that was one success story. Now the thing is hope versus hype. Many a times, like I said, many of these things are overrated, maybe because people are too excited about it. But after spending so many years, I know what to expect, what not to expect. And even if I get some extremely good result, I would still take it with ease. I wouldn't really, walk to moon and come back or something like that, right? So, because I already talked about this, when it comes to drug receptor binding, the contribution of water is extremely important, and at times you should look for algorithms where the water treatment can happen. And of course, OpenEye also has got very interesting tools, SHMAP and Shibaski. Very interesting tools. You can actually treat those strategically located water molecules and predict the potency or rather binding constants with great accuracy. I have not used them myself, but I know how to. I have attended the sessions, and they're amazing actually. And of course, I'll again skip this. You all probably know how drugs interact with the receptors, the forces of drug receptor interaction. Again, for understanding these, you should understand the chemistry of molecules which you are designing or which you are working. So that is very interesting. And I mean, the question is, how do we simulate this in silico? And so as you are doing it, so that understanding will help you in taking decisions as to what should be whether a particular operation. I mean, there are potentially say 4 or 5 choices which operations you can do, but based on your understanding of chemistry, you probably will do 1 or 2, and that's where you will stop. Meaning a simple thing as to when you talk about secondary amides, most of the times the secondary amides are always in the trans configuration. But when you build a structure, and if that structure turns out to have a cis amide, it is very highly unlikely that it will exist in the cis amide form. Not that there are no molecules which will exist in the cis amide form, but then if you do not know that an amide is likely to exist in the trans configuration most of the times, and if you build the structure wrongly, maybe when you do the conformational search, it will be taken care. Or maybe if you don't do conformational search, probably it is not. Again, depending on which method of conformational search you use, you don't know whether it will be taken care or not. Likewise, when it comes to treating the molecules, understanding of PK is very important. And so if you're talking about pH 7.4, you have an acid, and while docking the molecule, you are not ionizing it. Of course, most of the softwares, including OpenEye, they have the tools of taking care of the ionization state, because it's very important. So understanding the concept of PK and understanding the importance of ionization, like I said, the ionizable groups are very important because they will give that sensing ability to the molecule when it is approaching to its receptor, right? But again, these are the same molecules which are likely to cause problem when it has to cross the cell. So then they will be useful for solubility, but permeability, it will be detrimental. And that's where, as a molecular modeler, you have to take a call whether to use a particular group or use the bioisostereochemical group. And this is where the design part or the creativity in design part comes in picture. And understanding the molecular dynamics or the flexibility part on the macromolecular target site, again, you have to understand it thoroughly. And of course, for that, you need to have a thorough understanding of primary structure, secondary structural elements, the tertiary structures. Quaternary structure we rarely speak about unless that the receptor is exists, or rather it has a biological assembly. I mean, many software, they do have things to take care of this. I mean, nowadays, if you have to prepare a protein, there are defined algorithms. You just have to click one button and it will do it for you. But when we were working, we had to do it all manually. Again, I'll not describe that, but that was a tedious task. And you have to, and sometimes you try and minimize the protein and it will just open up and make a straight chain. Meaning it will make a chain instead of a defined 3D structure. So there were problems with the crystal structures, but nowadays we have got very high resolution structures. So again, when it comes to the resolution of the structures, which three-dimensional structure to use and which not to use. So anything beyond 2.5 angstrom resolution is good for nothing. You should not use it. Nowadays you have structures as low as say 1 angstrom resolution. Those are fantastic structures, so you should use them. So again, there are guidelines or there are rules when it comes to selecting, if you have a choice, selecting the right structure for your work. Ideally, if you have got, say for kinases, there are multiple structures for the same kinase bound to a different ligand. So ideally, you should be using multiple structures, because if the ligand is structurally diverse, the shape of the shape complementarity is going to be different. And understanding these things are again very, very important, as in it's not as straightforward. You download a PDB, throw it to preparing the structure, you prepare your molecules, and then just make them dock by again the algorithm, the force field, again the scoring function, whether you are using multiple scoring functions and how that scoring function is doing. Again, all those things we need to really understand. So although it's I tend to believe it's a magic wand within all the realms of whatever has been offered so far, meaning whatever we know as far as the capabilities of these molecular modeling softwares. So one has to take it with a pinch of salt, meaning one has to be really patient in selecting the right stuff or doing the right set of operations than doing anything and everything and getting nothing. Right. So understanding the structural flexibility where the molecules, the macromolecular targets can also adopt conformations and eventually get into a shape which is slightly different than what otherwise one would think. And this is where that induced fit model, Schrodinger has got excellent tool, although others also have got partial provision or rather provision for partially incorporating the induced fit by changing or by considering different rotamers of some of the residues lining the binding cavity. So these things are again very, very important, and understanding the crystal structure versus solution structure and their utility is central to understanding how these structures can be useful in terms of using them for doing the studies like docking studies. This is another paper. So after I came to NMIMS, we continued working on the human IMPDH. I got one nice project from DST SCRB, and we could actually design some very interesting. I mean, it's a difficult nut to crack. This target is a difficult nut to crack. We were only 4 or 5 groups working all over the world on this IMPDH, and my group was mostly working on human IMPDH. There is other group in US, in Boston, Mercer University. They were working on bacterial IMPDHs or parasitic IMPDHs. There is one group in IIT Ahmedabad, so they're working on Helicobacter pylori IMPDH. So I actually collaborated with almost everyone except this US group because Lisbeth was too busy. But then her students, her postdocs is where I collaborated, and we got extremely good. I mean, I wouldn't say extremely good. I would say moderately good or moderately potent bacterial IMPDH inhibitors. And I also collaborated with somebody in University of Cape Town in South Africa. He helped me find another collaborator in Europe, in one of the universities in Italy, and University of Florence. So we actually could put a lot of things together and did with whatever was accessible, whatever limited resources were available. So again, the point I'm trying to make that if you decide to do something, nothing is everything is impossible. Everything is possible. You just have to have passion for doing that. And of course, the computer-aided molecular design has helped me a lot. Although most of the papers you would see only small part of computer-aided molecular. So I'm just molecular design. So I'm just being realistic. I'm not just overemphasizing that I'm not just making up things like this is where computer-aided molecular design helped me like that. But it did definitely help. But it's the human mind. It's our own thought process which led us to extremely good molecules. These are examples from one of my studies. This one is again a very interesting paper. We collaborated with this researcher Sneha Gandhi from Australia. I knew her from my pyramidal days. She was working with Zydus. So here we actually we undertook one very interesting project. This system XA antiporter, which is actually a transporter antiporter present in the CNS, and it has utilities in epileptogenesis or epilepsy in epilepsy as well as in cancer. And we tried to do some real cool stuff. So Neha did the homology modeling stuff and transporter modeling. Dr. Weber will agree with me. Transporter homology modeling is very, very, very difficult. And although software will give you the model, but then the utility of that model will be questionable, and particularly in cases where the template has less than 30% sequence similarity with the query sequence, and this is where things get out of your control. But Neha did excellent work. In fact, she could run dynamics for I think 500 nanoseconds or so on a supercomputer. It took her almost 2 months, like whatever time she had, and then we could put together this extremely cool paper, and we were very happy. And we just did not stop at the homology modeling stage. We actually designed the molecules, found out did the molecular dynamics, found out how they actually behaved, and then synthesized those molecules and got them tested. So we completed the story. We just did not stop at the computational stage only. So these are some of the results. There was this other paper which appeared in JMC during my postdoc. Again, this is mostly synthetic paper, but part of it I did the work which was like pharmacophore elucidation for dopamine D3 receptor ligands. Very simple stuff. I'm not saying it is some out of the world job or something. No, absolutely not. Very simple work. MOE was used for that. I'll again not get into the details so that we save some time for the demonstration. Then QASR based approaches. This was my first paper back in 2002, first paper in Journal of Medicinal Chemistry, first research paper as such. So Dr. Anamik Shah, which you probably are aware of him, he is a very good synthetic chemist, medicinal chemist. So he approached Professor Kulkarni, and I did the 3D QASR work. It was very good. We got some very interesting results. Of course, these pictures, again, I'll not get into the details of these pictures. Those who are aware of what 3D QASR is, they know. So basically, we tried to justify the rationality or rationale behind the design. So but then this was in retrospect. I must admit, I'm not saying that we did the molecular modeling and then they worked on the synthesis and then testing. No, it was in retrospect. And that's where we could find some good correlation. But then nowadays, if you see journals, JMC, which is the leading journal, they will never accept any paper just without the experimental result. Right? But then those were the days where it was all possible. But again, I'm not saying it was a good piece of work. But then nowadays, you won't be able to do something like that. Then in the same paper, we also tried to do genetic function approximation, which is very commonplace in machine learning and deep learning era. So it was fantastic. We had another software called Sirius 2. So we generated plenty of descriptors and eventually used them for generating these interesting 2D QSR equations, and then tried to correlate with the 3D thing. So coming to the next gamut of activities under the computer-aided molecular design prediction of physicochemical property. This one is from Swiss ADDMC. So this is again very cool stuff. It's freely available. You can, all you need is just a smile string and you'll be able to do it right away. It gives you plenty of properties, very relevant properties. So all the students, you must try. If you haven't already, if you don't know about Swiss ADDMC, please try that. You should also try Protox 2, which I told you about. Right, those are very interesting. I think this is what Protox 2. It will tell you, it will give you a very large number of toxicity properties, including immunotoxicity, carcinogenicity, mutagenicity. It will also predict the LD50. Although these I wouldn't worry about these LD50 predictions and all. It will just I would go with the other predictions when you I haven't shown it here. But this is some real cool stuff. You should do that. There are tools available for blood-brain barrier penetration. So if you're trying to work on some CNS drugs, then those tools can be potentially useful. And then drug repurposing is another area where I have been working since my PhD days. Wherever I got a chance, I tried to work on. We in fact have a physical library of drugs, around 125 or 130 odd drugs. Whenever we develop a new assay, usually we'll screen the molecules, all the drugs, and then we try and find out if we get some good results. Last year, we published a nice paper in Indian Journal of Chemical Society, or Journal of Indian Chemical Society, on breast cancer repurposed. So out of 27 drugs, well, 60 drugs, we got around 11 drugs, very interesting results. And then we just shared, or rather shared those things. So this was the paper which I was talking about for Ebola using OpenEye scientific software. So this one is the picture generated from rocks. So there is a protein called VP35, which is a viral code protein in Ebola virus. So a molecule, the crystal structure of that protein along with a ligand, VP35 inhibitor, was reported. So we took that VP35 ligand and then did the ROX and EON studies on that. And for the screening, we used the drug bank database, from where we could try and find out the shape matching or shape similarity and electrostatic similarity. And this is what the outcome of that. And we proposed some of these molecules from drug banks. Some of these were NSAIDs, some of these were anti-diabetic drugs, some of these were, I would say, some of these were NSAIDs actually. Some very interesting stuff. So we actually proposed, and some of these were the actual experimental drugs, and that's how we could publish this. This was again another drug repurposing campaign where we tried to collaborate with a researcher from Malaysia, Dr. Yisu. Now also we have in fact communicated one very interesting paper. Maybe I'll talk about it later. Okay, so the thing is, did any of this thing really work? I mean, I can go on talking about I did this, I did that. This was so fantastic. This was nice picture. Ye, wo. I can talk, but what about it? As in, did it really work? I mean, that's exactly where recently we have got this. I mean, 6 months ago, we have got this US patent granted for the molecule, which we are going to take it for phase 1 trials, which will begin. The synthesis, CGMP synthesis of that clinical candidate is done. Now the formulation will happen in March, in March, and then eventually in April, the study will begin, phase 1 study. Right. So again, just the probably take-home message, when it comes to CAMD, despite the limitations and pitfalls, it has emerged as a trustworthy discipline. Now, you take any major pharmaceutical company or even the minor ones, smaller ones, everyone will invariably use some or the other type of computer-aided design. I'm not just saying about small molecule design, even the antibody modeling has become very popular. In fact, this software which I'm going to talk about, molecular operating environment, they do have antibody modeler module, and then there are a lot of things. As in, I would suggest you venture into area which are more complicated or less explored. The rewards will be much higher, and this is the age where you can spend time and you are learning at a fast pace. So you should try out something very interesting stuff like that. You are already doing it. I mean, I saw these 2 posters and amazing work, and of course, the synthetic chemistry, it should, whatever you do, it should be supplemented with synthetic chemistry or synthetic medicinal chemistry, just to test your hypothesis. So it has emerged as a good, very trustworthy discipline. Several success stories And then with changing scenario on the computational or hardware part, on the software part, the introduction of machine learning, deep learning, all of these have actually done so much to the whole thing that essentially people use it for to their advantage. But again, like I said, you have to be realistic when you have to work with these techniques, and this is extremely important. And you should be a good chemist if you're working in small molecule drug discovery. Of course, chemistry is everywhere. Even though you are working with macromolecular discovery, unless you understand why proteins aggregate, and you will not be able to find out a solution for that, right? So this is where understanding chemistry is extremely important. And with this, I will just stop here. Exactly 1 hour, and I am very happy. We will have at least 1 hour for the demonstration. Now, for some because of some technical issues, although we talked about OpenEye, but I'll be for the time. I mean, I did not want to disappoint all the eager participants that they are going to see some demo. So we are going to use the software which I have access to. We have a licensed copy of that, but we will be organizing a separate session for NIPER Guwahati students. Probably I have promised 1 day session where I will be demonstrating different aspects of OpenEye scientific software, including the ones which I talked about, ROX, EON, and then OE docking, extremely important. In fact, before I get into the demonstration part, recently there was this drug discovery hackathon last year. So we actually came up with a very interesting concept called peptide mold. And of course, why is that? Because if you talk about the targets which are available for intervention of SARS-CoV-2, so most of them, they are like there is 3-CL protease, there is PL protease, pepin-like protease. So when you talk about protease, so their substrates are peptides, right? And in fact, the Pfizer molecules which have been probably in phase 2 or maybe phase 3 trials for SARS-CoV-2, which are I think 3CL 3CL pro inhibitors. So they're all peptidic inhibitors, and that is the case. I mean, peptidic protease, the molecules will always be peptidic. So what we tried to do was we generated a library of 160,000 tetrapeptides, meaning you have 20 amino acids, right? So 20 into 20 into 20 into 20. So that is 160,000 peptides. So we process that for all the charge calculation, for all the ionization state calculation using OpenEye software, and then that library was further subjected to the conformational search, where for individual peptide we generated 200 conformations using Omega tool in the which is the tool available in OpenEye software for generating conformations. So by by default it generates 200 conformations, distinct conformations. So there are criteria. So you can imagine 160,000 peptides into 200 conformations for each peptide. So we actually worked with 32 million conformations of these peptides. Now we had a choice as to now why we did that. So so what we did was all these 32 million peptides were eventually put inside the so we worked on both the proteases, 3CL Pro as well as PL Pro. And then, so you can see 32 million dockings in one, 32 million in other protein. And then what we did was after all the dockings were done, we had our own issues working with so large set of conformations, or in a way individual molecules that way. So then what we did that in part, like in a set of 20,000 like that. And then after this whole thing was done, so for each of these proteins, we got we selected top 100 peptides. Then we did from the docking study. Then we selected structurally most diverse peptides, and then used their binding conformations with the say PL Pro as well as 3CL Pro separately, and then develop the pharmacophore from that, and use that pharmacophore for screening library of natural products, because that was the mandate of that particular challenge. So again, that library itself was 158,000 molecules, all the natural product. So we could actually get it, download it from one resource, one of the paper supplementary information. So we processed that and tried to accommodate molecules which were between molecular weight 200 to 800, and rest everything we removed. So we were left out with around 142,000 natural products. So use the develop pharmaco for each of these individual molecules, and screen pharmacophore screening, which we did, and then we came out with a set of 10 top ranking hits, and then we further docked them in that particular structures, and eventually proposed. So this was the outcome. Now, where is the peptide mold concept comes in? Now you see the proteases. They are, of course, they are proteins. They bind peptide substrates or proteins, right? Because their job is to chop off the proteins. So, and when you talk about a peptide, say a tetrapeptide having say 4 amino acid residues, so then that peptide can adopt various conformations based on the shape of that particular site. So then we try to take the snapshot of that particular. We try to do it the other way. We try to take the snapshot. This is like a clay. You have a clay, you put it in the mold, and that shape, you get that particular shape. So we did that and eventually use those snapshots, align them, and find out how, what are the features responsible for binding, and use them for. So amazing, a lot of work. We worked for like 2 months, 6 of us, all the students, and we also had access to, as a part of that hackathon, we had access to CDAC, their computational facility, and we could do a lot of things. We also independently did that conventional way. We took all those molecules, meaning all the natural products, 142,000, and individually threw at the for the docking, and then tried to see whether there was an overlap. There was some overlap. Of course, we expected that because it's a huge library, and then the approaches were different. But what I'm trying to tell you is that was one exercise which we, we did not leave any stone unturned. Although we haven't really communicated it, but we will soon be communicating those results as a new concept, peptide mold. So it's an unpublished result, but I just gave you a brief overview what we did. And this is where I will stop as far as lecture is concerned. If you have any questions, please feel free to ask, and then we'll move on to the next part, that is the demonstration of basic molecular modeling exercises.
Thank you, sir, for a very nice lecture. I think it is better that we take questions towards the end so that the demo can be completed nicely.
So then in that case, I will just share my screen and move ahead with what we are doing. That is the demonstration. So I will just stop sharing and come back to sharing again. Can I share the screen here completely?
Yes, that should be possible.
Yeah, I can share it. Is it? Okay, now you see the PowerPoint presentation, right? Now I'll just open the, do you see the MOE window?
Yes, sir, we can see that.
Okay, perfect. So again, I have used different softwares, and I'll just close this so that you don't get confused. So this is the window of MOE. Although you see only 6 or 7, or probably what this is total 8 menu items, but everything is hidden inside. And I have already opened this particular, maybe I'll just open it. So on the right hand side, you have different quick access menus for the system, for aligning the views, and then for building and minimizing. So everything is there, and all of these functions are also accessible from these different windows, right? And the way MOE works is if you are working with small molecules and if you're working with multiple molecules, the best way to do this would be to open a database, and this is what I have already done. So this is a database where I have actually drew two structures. One is 17 beta estradiol and the other one is tamoxifen, which is the selective estrogen receptor modulator. And of course, 17 beta estradiol is the hormone which binds to both estrogen receptor alpha as well as estrogen receptor beta. But again, just getting into now, I would want students or the participants, if you can ask questions in terms of when I say, do you know how to use smiles for, or Dr. Weber, you can probably just update me. So the students, they already know how to do simple molecular modeling stuff, or what is the state as in?
Because we are also forecasting it live, we can consider that they are very beginners and you could go in as many details as you feel.
Perfect. Thank you. All right. So like I said, we'll have a separate session on OE software modules, and I promise probably one day full day I will spend explaining all the things. So, but here whatever is accessible, and I did not want to disappoint the audience. Okay, coming to the basic molecular modeling stuff. So the first important thing is structure drawing. Now there are various ways by which you can draw structures, and every molecular modeling software will have some or the other functionality where you can sketch or build the structure. So one of the easiest way of building structures is actually getting the smile string of that, which is the one-dimensional representation of the structure, and then use that smile string for converting it into the structure. And you can do that by many means. Either you draw it in some structure drawing package. Maybe I'll just show you ChemDraw. I'm sure you are aware of ChemDraw. A lot of people use ChemDraw, or any structure drawing package will have access. So now my computer is connected to the internet, and I'm just converting the name, say tamoxifen. I'm just giving the tamoxifen, so the software will automatically convert it into the structure. There are ways by you can also go to say the Wikipedia monograph. Maybe I'll just show you how to get to the structure. So this is tamoxifen. So everyone uses Wikipedia monograph for some or the other thing. Say for simple stuff like a drug whose structure is already known and stuff like that. So if you go to the bottom of the Wikipedia monograph, so at the end, towards the end, you will see the SMILES notation for that, which is simplified molecular input line entry system, which is the 1D representation. So if you click on this, you will get a one-dimensional string of that particular structure. So there are conventions to write that. You can read more about it again from the Wikipedia monograph. So simply, I'm just going to take these SMILES and copy it here, right? So then I will go to MOE. Although I have drawn this structure, but I'm just demonstrating that. So I will go to Builder. So the Builder will open. So there is a provision for entering the SMILE string. So I will just say Control V. It will, the SMILE string is pasted. Now this smiley is activated, right? So maybe I'll just say Control Z. I'll delete this. The smiley, there won't be any smiley. Right, the moment you pasted the smiley, that means there is no issue with the smile string. I just click on this string, and then it will ask me whether what name you would want to give. So I will say tamoxifen, and then just take this out, all of it, tamoxifen, okay. You see, within a fraction of a second, it has converted into a nice three-dimensional structure. Now, if you want to see this structure in different representations, so I'll probably use the ball and stick method. I can use the only stick method. I can also use ball and line method. but then I usually prefer the ball and stick or only stick. But again, that is individual thing. I can hide the non-polar hydrogen, so that structure is. So this is the three-dimensional structure. I can also display the charges, atoms, charge. Now see here the charge is 0, 0, 0, 0, right? Because I have used smile string and I pasted that. So when the structure was converted from 1D to three-dimensional, it did not really give any charges. Now, if you remember, I told you, if you were blindfolded and if you were to walk in a room, you will sense it. So if you do not have that sensing ability, you will not be able to do anything, right? And this is where the charges, which are very important as far as electrostatic interactions are concerned, they play extremely important role. So whenever you convert or whenever you build a structure, convert a 2D structure to 3D structure or convert a 1D string to 3D structure, the very first thing you should be doing is assigning charges. Now, again, I'll just hide these charges. Right now, how do I assign the charges? So there are, again, every software will have its own way of doing it. So I will just get into say potential energy, or I would say energy minimize. Again, this is not a problem. So here it will automatically this is a newer version of Mo, so it will automatically calculate the force field charges. So you can actually get into say input all atoms, then other things you don't worry about. Then it says force field. Now, because it's a small molecule, it has automatically selected, because MMFF94X or its variants, they are good for small molecules. If it is a protein molecule, there is a different way of doing it. Again, I will show you that how to do it. So I wouldn't worry about this. Atomic partial charges appear to be incorrect because we have not calculated it. So all I do is, and then because we are minimizing the structure, again, many times when you build the structure, the geometry may not be perfect, although here it is fine. But at times, if you are sketching it all by yourself, then at times it becomes difficult. So to optimize the geometry, you always energy minimize. So again, there are methods of minimizing energy, but many times the software will have its own default settings, which will be much better. If you want, you can change those. Otherwise, it is fine. Say the gradient. So I will, because it's a small molecule, I'll probably go with 0.001. That is the kilocalorie per mole per angstrom, angstrom square. Kilocalorie per mole angstrom square. In the sense, this is a termination criteria. So when it minimizes the energy, so there will be energy associated with that particular molecule, which is a function of the force field and the force field terms and the overall atom types or overall constituents of that molecule. And then eventually, when you minimize, so this energy will be minimized. Now, again, you have to understand that every system in the universe tries to attain the state of minimum energy, and this is exactly what is done here. So then when you minimize the structure, so initially suppose the energy is 100 kilocalorie per 100 kilocalorie, right? So per kilocalorie per mole. Then in the next cycle, the minimization algorithm will bring to say 66, and then again it will go on dropping. So, but what is the point where it will stop? And this is where it could be either number of iterations, or it could be the change in the RMSD, right? RMS deviation between the two successive steps, and this is that criteria. So what I will do is I will just say OK, and it is done. Before even now, my computer is relatively fast. It has got 32 GB RAM. For 4 GB, it will take maybe a few more seconds, which is fine. Then I will again show you the charges. Now it is actually, I did not select the force field. So maybe I'll just select the force field and get you there. Just hold on, I'll probably. Should be okay. Fixed charges. Yeah, now it will be fine. You see, the fixed charges were done. So basically, charge calculation is an important step after you build the structure. Without the charge calculation, it is of no use. If there are no charges, you will not be able to get anything, any meaningful thing out of it. Again, like I said, you change the force field and the charges will be different according to the force field definitions. But again, force field is a collection of all the energy terms which will be used for building or for getting that particular, for treating that molecule. Like I said, everything you are trying to simulate in a computer, so you have to instruct the computer separately to be able to treat it the way you would want it to be treated for getting some meaningful results, right? So likewise, every software will also have its own version of taking care of the ionization states. Again, I will not get into the ionization states here. You can actually suppose if now if you see just yeah. So now you see, I have selected this nitrogen atom. It's a tertiary nitrogen, right? So here this it's 0. The formal charge is 0. The moment I say +1, it will automatically add the 1 nitrogen. Now it becomes cationic nitrogen, right? So you can actually now here you don't really have to do it all by yourself in the database. You can it will be done automatically when you instruct. I say I do not want, I just say it is 0 charge, no formal charge. So likewise, it will be done. So the next thing I do is after I calculated, like I build the structure, I calculated the charges, I assigned the force field, then calculated the charges and eventually minimized it. So my structure is ready with bare minimums to be able to do the next set of events, which includes conformational search, which also includes other types of studies, including where you would want to use it for some alignment or stuff like that. So likewise, what I have done is the next thing I would do is I would add it to a database. I have already built a database and I have added it to the database. So how would I do that? I will just say new entry, and then it will ask me and it goes in there, right? So this is one thing I have already done. Now you can actually close this file and not do anything, meaning that molecule once put in the database will be there. It will not be deleted. So whenever you would want it, you just say double click and it will appear in the workspace, right? So now what I'm going to do here is you already have tamoxifen with you, and I'm going to show you one very important thing, that is flexible alignment. Now, when I say what I have done similarly is I have built 17 beta estradiol structure. Maybe I will show you that structure first. So this is a steroid structure, estrogen, one of the major estrogens. This is 17 beta estradiol. You've got 3 hydroxy group. Ring A is aromatic ring, and this is the 17 beta hydroxy group, right? So this is your structure. And if you see the ring fusion, this ring B and C, it's a transfusion. Ring C, ring B and C is transfusion. Then this is ring C and D is again a transfusion. If you see, this is ring C, this is ring D. If you see, this methyl is up, this hydrogen is down, so this is trans ring fusion. So likewise, you can just make sure, again, I have drawn this structure using smile string, so it should be okay, but you should always check out, just the way I told you about amide bond, cis amide versus trans amide. It's always a good idea to keep a tab on that. Suppose if I want to modify this structure, so then there are possibilities by which you can, so I select this, I put CO2. So then it has actually given me the COOH group. If I want to say that this COOH should be ionized, so I just say COO minus, the hydrogen is gone here. Likewise, right? So same thing, I can individually build the structure and then put it in the database. You can also import an SDF file directly into the database and completely treat those database molecules using the functionalities available under database, which are seen here. See, now you see compute molecule, then it will ask you wash. So many times when you actually get the SDF file, so it is possible that that SDF file, it could be commercially available molecules, commercially available database. So then it is possible that that SDF file contains a salt of that molecule, meaning say atorvastatin calcium or other hydrochloride salts. But when you work with molecular modeling operations, you would want to get rid of those small parts, and that's where that process is called wash thing. And then you can also you have quick prep. So quick prep will basically it will try and do all the necessary operations which I individually explained you, but here you can do it in the database. So here, of course, this quick prep is applicable to the ligand. Here you can, I mean this whole functionality is available for preparation of protein. So I will show you this thing separately. I will show you for the molecule partial charges. So it will ask you which force field to use. You can actually select the force field and eventually use it. So I'm selecting MMFF94, and the whole thing can be done. And then whether you would want to write it in the same field or same column, or you would want to do it in the separate one. And then adjust hydrogens and lone pairs as required, and it will automatically do it automatically. I mean, within a fraction of a second, without even you noticing something happen. Right. So likewise, you can bring in molecules containing 10,000. I mean, databases containing 10,000, 100,000, whatever the memory of your computer can support, it will give you. Now, what I'm going to show you is the flexible alignment. Now, many times what happens is, suppose you have a crystal structure ligand, say aceclofenac bound to COX-1 structure, or aceclofenac bound to COX-2, or celecoxib bound to the say COX-2 structure, right? So in that case, that crystal structure conformation, you would want and see whether any of the molecules are aligned. Many of the molecules could be a repurposed drug or your own molecules, whether they have the capability to align onto that particular molecule, which is the active molecule, and whether I can then test those molecules, my molecules, for a particular indication. That's where flexible alignment comes handy. Again, like I said, the receptor will not have eyes, the molecules will not have eyes. So as long as there is structural similarity and of course electrostatic similarity, you can believe that those molecules which are similar in shape and to some extent more or less similar in the electrostatic distribution or electrostatic profile, those molecules are likely to bind at the same site and likely to exhibit similar activity. Maybe more, maybe less, we don't know. But then that is hard to predict using these molecular modeling tools. And this is where we would be using flexible alignment tool. But then how do you make sure that your crystal structure conformation does not move, and only the molecule, the test molecule which will get aligned will move? And this is where I'm going to show you. So assuming that 17 beta estradiol, of course, it's a rigid structure. Even if I don't constrain it, nothing will happen, meaning it will not really change its shape or something. But I will still constrain it just to show you. So what I'll do is I will just fix this molecule so that none of its atoms, individual atoms, will move. So I say potential. I've selected the molecule, I've said potential fix, and then I just deselected it. Then I will take the second molecule. Tamoxifen, both are tamoxifen. I will take the second one. It says clear system before loading data, no, so that this molecule will be also seen. Now, it looks little clutter. So what I will do is I will say hide the non-polar hydrogens. So everything except this hydroxy hydrogen, everything is, and this nitrogen, they are all kind of gone as in they are hidden. They are there, they're not deleted or something. Then I go to flexible alignment. Now I say flexible alignment, it's here. Okay, it's a very powerful functionality, and even most of the softwares you will get this flexible alignment functionality. In case of OpenEye software, it is ROCks, or rapid overlay of chemical structures, which also will have the pharmacophoric components embedded in that. Here also you have pharmacophoric elements. Now you see the default weights are given. Suppose if you have a reason to believe that the aromatic rings, they should be kind of more aligned or so, then I can select this. So then again, you can change these weights. That is also fine. So that will give more emphasis to that individual term, right? And then there are other things, including the config, how many configurations will be saved, and the gradient and the RMSD, meaning if the unless the RMSD difference is less than this, the structure will not be saved. So likewise, you will do that. So I say OK here, and then I will probably just say flex align 1, because I already have a database like that. And rest other, I can also have rigid body, I can also have flexible alignment, and then I just say OK. See, now the molecule that steroid molecule is not moving because I have fixed it. I do not want it to disturb because it is the crystal structure conformation. I mean, it's not, but I'm just assuming it is a crystal structure conformation. I want to demonstrate how it happens. It will take some time, although my computer is quite fast, but it will still take time, and it will complete those 100 iterations or so. So what I will do is I will stop, and I will directly take you to the web database where this alignment is already done. So I will just stop this, and I will close this. I will directly open the database, which was already flexibly aligned. So, so this is how it. This is the top. Again, this is not. This is probably the best alignment by the criteria which is given here, including. Now you see there are different criteria, including the energy when you align. Then you also have a criteria called S. That is nothing but it's a parameter which will give you this parameter should be as low as possible. So this gives you an idea in an attempt to align one molecule onto the other, whether the second molecule is likely to have strain in the structure, meaning if the molecule energy is higher, then at the biological level it is not likely to happen. And this is where this criteria will be set in such a way that, I mean, it's automatically done. It is set in such a way that it will in a way remove that particular alignment. So what I'm trying to tell you is it will automatically arrange the best alignment on top and followed by the next ones. So I'm not worried about the other alignments. I mean, I can always take a look at top 5 or so, but I'm just going to hide the say non-polar hydrogens. So now you see what it tried to do was it tried to adopt the similar shape. Of course, the tamoxifen structure is kind of a rigid structure as well, because you have a C double bond C like that. So there was an alignment, nice alignment here at the aromatic ring. Then there was also an alignment on the oxygen side because tamoxifen has this ether linkage, whereas 17 beta estradiol has this linkage. So what I'll do is I'll probably just show you how they align well. Although this is in the element color, I will show it in the and then I will show it in the color, one particular color. So one molecule is one color. I select the other one, and then atoms in different color, say probably green or maybe blue. See, now if you look at the features in this particular, maybe I'll just show the, yeah. So then this gives an idea as to which are the features which are likely to align. So you may have a crystal structure ligand, you may have your own design. All you have to do is try and align with the crystal structure ligand and see. That's where the design part comes in, your intellectual contribution comes in. You see what changes in the structure will be necessary to maximize this alignment. Ultimately, the simple rule you have to, you have to follow. similar looking molecules, similar molecules having similar shapes are likely to bind to similar targets. Very simple thing. So you can actually start this work using any known kinase inhibitor, which is a blockbuster drug and whose crystal structure is available. I mean, not necessary that you always have to take the crystal structure confirmation. Even if there is a single crystal X-ray crystallography structure available for your small molecule, you take that or build the structure, do the conformational search, take the minimum energy conformation, freeze it, and then use your molecules to align onto that. There are various ways by which you can do it. All you have to do is trial and error, and you will hit something very interesting. So then once you see this alignment, then you probably would want to change something in the structure in your molecule. What if I do this change here? Will that improve the alignment? Very much possible. And this is where understanding the chemistry is important. And again, you have to, when it comes to electrostatic features, you have to make sure that an electronegative feature should be placed at where the other electronegative feature will be present in the active molecule. So likewise, you have to then think from the chemistry perspective, whether if I put an ether, will that work? Whether or do I put an amine, but then that amine can be ionized at physiological pH, but ethers will be neutral. So will that make a difference like that? And then you also use the concepts of, I would say, bioisosteres replacement. In fact, OpenEye has got a very, very powerful bioisosteres replacement platform, wherein you have to just select your say potent molecule, say a kinase inhibitor, which is nanomolar or picomolar potent. Then you have to select part of the molecule which you would want to replace with a bioisosteric moiety. So they do have a very huge database of bioisosteres containing few million fragments, and then that particular molecule, that part of the molecule will be put. All those bioisosteres from the database will be put in there, and eventually it will give you a molecule having the best bioisostere in terms of the steric as well as electronic distribution. And this is how you go on replacing part of the molecule and come to a very, very new structure, which is not only similar looking in terms of the pharmacophoric features, electronic features, but it will also be structurally novel. I mean, the one which I showed you is very, very simple form of what you call it as flexible alignment. So as a student, even if you do flexible alignment exercise, for some of your own designs or maybe known molecules, known drugs, believe me, you will definitely be able to come out with something very interesting. And then you essentially get into synthesis, or you use the commercially available compounds. We have done that previously, do the computer-aided molecular design job, and then essentially select molecules which are commercially available, get those molecules and eventually test it. So you don't have to do the synthetic work as long as you have funds available. In fact, we published a very nice paper in Journal of Cellular Biochemistry where we worked on HRAS, which is one of the sought after targets in cancer chemotherapy. So we also not only that we work with the mutated version of HRAS because that's what is observed. There are 3 major mutations. Then what we did was we actually did all the docking, the native ones as well as these mutated versions. So we also took combinations of 2 mutations at a time, 3 mutations, all 3 at a time, and single mutation at a time. Did extensive computational work, including mostly molecular docking, and then we ordered those chemicals. I think we ordered around 8 chemicals, out of which we got 2 compounds moderately potent. I'm not exaggerating. I'm not kind of over promising that we did this, we did that. Whatever we got, I'm very humbly I'm explaining that we got moderate. I can share that paper. I think it was in 2017 or 2018. Amazing work the student did. Of course, I was there. She was from biology or from bioinformatics side, but then I helped with the all of this modeling stuff and that. And we could actually come up with very interesting molecules. So again, what I'm trying to tell you is it is very much possible to do things which you can do within the realms of their limitations and capabilities, right? So this is one very simple thing about ligand based design. They also have a very powerful pharmacophore module here. Likewise, you also have most of the softwares will have again pharmacophore based design is very powerful technique in terms of the speed and the reliability with which you can get these searches, meaning the hits, and you can actually use, and you can also combine these pharmacophore searches with the hits from the structure based searches, and you can have a combined result, and you can increase the probability of success more. So I'm not again going to go into the pharmacophore here. You can elucidate, you can actually build a query. So so again, what I'm going to do is I'm going to use a particular query, say CHD, and then I say consensus pharmacophore. So it will give me a lot of these things, but then I can manually select the features which are common. So we have a control. It has got a very good pharmacophore capabilities as well. I can use this as well. So manually, so again, unless I have the understanding of the chemistry, I will not be able to do a good job in pharmacophore searches or pharmacophore elucidation as such. Of course, this is not an elucidation actually. This is a query building. There is, if you have got a molecule set of molecules, active molecules, inactive molecules, you can put them in a database, elucidate the pharmacophore, it will be automatically done. And then you select, you can further edit the query and use that query for the searching of databases which will match the pharmacophore. It's a very powerful tool, and many softwares has it. OpenAI has it. Amazing stuff. I just love it. Believe me, I can't thank Dr. Vaibhav enough I have been so busy with my academic work and other stuff. I haven't really used these softwares for a very long time, and now that I'm just getting excited. Believe me, it's almost 20 minutes to 2 hours. And morning I had 2 hours lectures. I'm so tired, but I'm very excited, and that's why my energy level hasn't really gone down. So having said that, what I'm again trying to say is there is so much possibility that you can do with simple things. I am not saying you have to do all hi-fi stuff, this and that, homology modeling, that. You can do that. You are students, it's a project, if you're working on that project, you can do that over a period of time. But as an exercise, as a simple learning tool, you try and simple things, believe me, you will get to something very interesting. I'm not saying that you will discover a drug right away or you will repurpose a drug right away, but that understanding what you get is going to be very important to you to to leap into more advanced calculations or more complex versions. Dr. Vaibhav is there. He works in free energy perturbation, density functional theory, I guess. A lot of highly complicated stuff he does. I don't do it. I am not an expert. I have not done it. My part is only at the application side, and that too simple stuff. But I know what I do, and I do it very religiously in terms of taking or inferring, meaning I use it to my advantage. I put my chemistry understanding and my overall understanding of the molecule to advantage, and that's where what we have done so far. Whatever project we have touched, we have actually got some good success. And of course, I'm not saying every molecule will become a drug or so, but at least we have got 2 molecules in phase 1 trials. I think that's very comforting. I mean, this is not that I'm well relaxed and I will not do anything, but this is where that's actually a motivation to do more. Again, the point as far as I have to tell to all the students, every simple thing, and take one step at a time, do simple things, understand these simple things and go to the next level. Meaning these softwares offer a large variety of capabilities, but you try simple things and then build onto the hi-fi stuff, including the homology modeling and stuff like that. Now what I'll do is I'll show you a protein preparation part. Maybe I'll just pull out some random protein structure, and then we can get into I'll close this database. I'll finish in next 10 minutes and then we can have time for the question answer session. So again here, if you go to a protein, you can actually search the PDB. I can take one, just a minute. I can do the PDB search actually, search PDB, but then probably I'll go here. Just hold on. I can download a PDB file and open it here, but I can also just a minute. Let me just figure that out. Load a protein sequence for or from the clipboard or paste. I'll probably download. I'll probably download a protein and I'll download a protein quickly, a PDB file. So you go to rcsb.pdb, rcsb.org. So 1JRH. So this is one of the files or one of the PDB IDs for the 1JRF. 1JRF. Or what I will do is just a minute. Lipophilicity. The COX2 active site. Let us download that. Structure of celecoxib bound in the COX2 active site. I will download the PDB file. Or I will take 3LN1. That's the I have to put it in the same folder where I am going to one of the folders, 3LN1.pdb file open. It seems to be C drive users admin. Just hold on. Copy, C drive. You can also search from here, actually. Let me see, 3. So don't worry about anything, just say default thing. So it actually, the protein is loaded. Now here, if you see, it's probably a dimer. Okay, so now what I'm going to do is I'm going to prepare this protein. So this is where the quick prep thing will come into picture. So again, I don't want to go on explaining here. this protein preparation part will essentially take care of many issues which are associated with the protein structures. So some of the many a times this protein will not have certain parts present, some loop, because loops are so flexible they do not really appear in crystal structures, and that's where adding the loop adding the loop based on the algorithm, underlying algorithm, it will do that, and it will also essentially take care of some issues related to say rotamers, and then there are many other things, including the water molecules and things like that. So now it is protonating the residues. So all the ionizable residues which are present, which are accessible, will be kind of protonated, and then it will take care of all the other issues. It should get over soon. I'll just finish this and then show you. So again, these are essential tasks whenever you deal with any protein structure which you download from PDB. You have to prepare the protein structure, without which you will not be able to get good results in terms of when it comes to docking or other operations using that protein structure. It should take another minute and it should be done. And because these are solid state structures, so when the hydrogens are not in the 3D structure, so whenever the hydrogens are added, it will essentially cause bumping. So it has to, the software, the preparation algorithm has to take care of all those things. So minimization will happen and stuff like that.
I'm just curious here to know that did it generate the conformations for the co-crystallized ligands also?
No, usually all this, the algorithm will take care of only the protein part. It doesn't really touch the small molecule. It does not. It doesn't actually.
It says conformer generation, so that's what interesting.
Basically it is trying to look at all the rotatable, the rotameric states. Yes, asparagine, or even for that matter, histidine. Then threonine, serine. So it's probably going to take time. So, but again, what is important here is I'll just cancel this and try and show you. So this is one of the ligands, as in this is a carbohydrate, which probably they used for crystallizing. I'll probably go to another ligand. I don't know if this is the right one. There will be plenty of ligands present here. Or I can select the ligand. I can see one here. Probably celecoxib or something. Yeah, this one is celecoxib. So I'll select this and say ligand interactions. It's not getting selected. Just a minute. I mean, this thing is not complete. No, that's probably the issue. Somehow selected residues. Anyway, so the point, what I'm trying to say is this is the celecoxib bound in the COX2 active site. So when the operation gets completed, it will isolate the ligand part and it will show the interactions with the neighboring residues. And you can also visualize in this particular 2D interaction diagram. You can use this and put it in here, put it in the publication. I mean, not for the crystal structure ligand. Whenever you dock any molecule, you can actually use the tools available here to zoom in at the ligand binding site, how it is interacting, including the interaction energy and stuff like that. So again, the interaction energy will be a function of the force field which you use, and eventually you are interested in the relative values of the energy and not the absolute values, meaning whether the interaction energy is higher on the negative side when molecule X is there versus your crystal structure ligand. So likewise, you can actually have your own inferences, correct inferences actually. Meaning when you talk about docking score, whether -20 is good versus -12 is good. So it all depends on in that particular docking run when you prioritize or when you actually arrange them in the ascending order. So in that case, the docking score highest on the negative side will definitely good. And then the next molecule with the lower docking score. Likewise, you will prioritize, right? So you are not worried about -18 versus -12. If you change the molecules, the database, you will have a different docking score. But as long as the structure is same, as long as you do the similar profiling in terms of molecular docking, meaning the settings and stuff like that, so then you will be able to compare one ligand with the other in the relative term and not the absolute terms. So that's where there are a lot of things which we can actually talk about. So again, each docking program has its own version of placing the initial placing of the ligand, and whether how it is moving, whether it is allowing the rotation around the single bond, whether it is building say just the way it does in Schrodinger XP mode. It will have the core structure and it will grow inside the active site. So there are various versions, and ideally, as a person working in this area, I would suggest you should use different docking scores, and then take the consensus score, meaning you can probably just sum them up and say which one is the lowest or highest on the negative side, meaning minus highest number. Like that, you can take, and many softwares will also have consensus scoring function. And then many softwares will also have different algorithms for initial placement. So here you need to just do a lot of trial and error and find out which one works the best. Meaning first thing is validation, whether the settings of that docking program is able to reproduce the crystal structure binding pose of the ligand, crystal structure ligand. So that is your test. And whether the docking score which you get correspond to probably because that's the experimental compound, meaning say celecoxib being the known inhibitor, very potent inhibitor of COX-2, meaning it's a proven drug. It has been experimentally proved. So the initial validation part is important. Then you can use the docking algorithm and the settings for screening out your own molecules or commercially available databases. With this, I will stop. There is so much to talk, but it's already we are reaching 5:30, close to 5:30. And I really, I'm really happy the time management in terms of sharply starting the lecture at the time. I'm not surprised. It's Dr. Vaibhav, so and his other colleagues. So this is how you should be. You should respect time, and the same thing I would do. And if you have any question, please feel free to ask. You can write to me if you think I can answer the questions. I can always be happy to help. Okay.
Thank you so much for a wonderful talk and so many detailed explanations, first in the lecture and now with the softwares, and we look forward to a detailed demo in the near future. But this is now open for students to ask any questions if you have any. Let me see if we have anything on the YouTube channel.
Okay.
They are just appreciating how nice informative session. No question. I couldn't see any question so far. Yeah, there is one. Please explain the difference between hit and lead.
Well, interesting question and a very, very relevant question, I must say. Now, when it comes to hit is always hit will precede the lead. Now, you will convert the hit into lead. So hit is usually, see, many a times whenever you are working on a program, say anti-cancer drug discovery. So if it is a target-based program, suppose if you are targeting BCR-ABL, any kinase thing. So the first thing you would do is say carry out high throughput screening. I mean, that's typically done in big pharma companies. So their compound repositories and screen in the first assay at 10 micromolar concentration, and any molecule in this very first assay, any molecule which will show appreciable activity. So they will always have a cutoff, say more than 50% inhibition, more than 50% inhibition at 10 micromolar concentration. So now these are the molecules which you can very precisely call as hits, meaning you are looking for molecules, inhibitors of that particular target. You have done only one assay and you got some hits or some molecules which has shown some promise. But now the question is whether this hit has got appropriate properties as far as drug action is concerned, including appropriate pharmacokinetic properties, even the physicochemical properties. Because initially when these in vitro assays are done, the compound concentration like 10 micromolar will be usually the initial stock solution will be made in the DMSO, and then this molecule, meaning the stock solution, will be converted into the working standard in the sense working solution. You will dilute it to 10 micromolar and eventually use it. So the compound may have solubility issues. So then the next thing you will do is you will probably go with functional assays, meaning there could be additional assays where the molecule is likely to, its activity is likely to be ascertained, or additional assessment you will do. And then eventually, once you see that there, like I said, the whole drug discovery revolves around potency. So as long as, so after your initial percent inhibition data, they will generate the IC50 data. So as long as the molecule is, say, potent nanomolar inhibitor, they will take it to the next level where they will evaluate the, in so-called early admit studies, they will evaluate the solubility, kinetic solubility, many times thermodynamic solubility. Then they'll also look for permeability, CACO2 permeability. There are many MDCK permeability. Again, many of these are high throughput assays. So once they, again, there will be some molecules. So initially you had got say 1,000 hits. The next assay solubility, kinetic solubility, where you have a cutoff of less than, at least the compound should have 1 micromolar solubility. Again, some say 500 molecules are dropped. Then you go to the next level, that is permeability. Again, 250 molecules are gone. So then you go to the next level where you try and see, say, the CYP inhibition property, CYP induction property, or CYP phenotyping, whether the molecules are getting metabolized by CYP enzymes or so. Then again, some molecules will be gone. This is where you will go on, say, some molecules will pass all those early criteria, and eventually come to a stage where you say that this is a good molecule which not only possesses the potency, selectivity, it also possesses reasonably good physicochemical properties, and that's where you would further. So that is the second, the second stage. The same molecule which was earlier hit now will be called as lead, because it has come through various stages in terms of possessing the good right set of properties, but it may not have the optimum set of properties, and this is where it will further undergo a round of structural modifications which we call as lead optimization, and that's where they would the molecule will be further optimized, studied in animals for animal efficacy studies, and then eventually go to the preclinical stages. So hit will be the initial stuff, and lead will be after particular further screening, and then that lead will further undergo optimization to make it better.
Yes, I think that very well summarizes, and I hope that clears the doubt in the minds of the participants. So I don't see any other query coming. Anybody, last chance, anybody online would like to ask? Okay, I guess not. Hello.
Yeah.
Can you hear me? So with this, we come to an end of today's session. It was very well and very informative and very encouraging and knowledge. We found that our knowledge is increasing in the drug discovery area and how one can apply these methods to take molecules to phase 1, as Professor Kharkar has summarized. And in the morning, stalwarts in the fields have come and shared their knowledge with us. So with this, we come to an end for today. And tomorrow we will start sharp at 10 o'clock. And speakers from IIT Delhi, Triple IT Delhi, IIT Guwahati, Jadavpur University, and even Manchester, a speaker from University of Manchester will join us tomorrow. So we look forward to your participation and joining. So with that, we come to an end. Thank you all. Thank you, everybody.
Thank you so much.
Have a
Thank
good
you.
day.
Yeah, you too. Bye.